The universe may be teeming with intelligence, yet Earth could be sealed off by physics itself, an island no starship can ever reach. Not because aliens aren't out there, but because the cosmos might be built to keep every civilization trapped at home. So why has the sky stayed silent? Are we truly alone, or simply unreachable? Look up at the night sky and feel the contradiction. Billions of stars and not a single unmistakable visitor. If the universe is full of minds, why has it stayed so quiet? Are we alone, or simply unreachable? Across the Milky Way, worlds circle suns by the hundreds of billions, and many of those worlds are older than Earth. By every sober estimate, the raw ingredients for life should be common, and time has been abundant. So the silence is not a small mystery. It is a pressure against our assumptions. For a century we have been leaking radio into the dark, a thin and fading bubble that barely covers our neighbourhood. Our farthest probes are still, in cosmic terms, close enough to shout back to, and the nearest stars remain years away, even at light speed. The sky may feel intimate on a clear night, yet the universe measures intimacy with a cruel ruler. This film begins with a suspicion that is colder than any conspiracy and heavier than any hope. Perhaps the reason no one arrives is not a choice, not a treaty, not fear, but physics itself. The same laws that let stars burn with steady light may also lock every civilization into its own island of space-time. We will follow 4 prison bars that do not negotiate. Distance, the speed limit written into relativity, the energy required to approach that limit, and the fragile problem of surviving the journey. Each barrier sounds simple until you put numbers on it, and the numbers refuse to stay abstract. A light year is not just a unit of length, it is a unit of waiting. As speed rises, the universe does not merely resist, it punishes, turning momentum into debt and fuel into impossible mathematics. Push harder, and time itself becomes strange. Mass becomes stubborn, and the promise of almost light speed becomes a trap. Even a civilization with vast power must still pay in energy, in mass, and in the need to slow down again at the destination. And if someone does attempt the crossing, the space between stars is not empty in the way our eyes imagine. At high velocity, a grain of dust becomes a projectile, a thin gas becomes a storm of radiation, and shielding becomes both salvation and burden. The void turns hostile not because it hates you, but because physics is indifferent. Then comes the slow alternative. Generation ships, missions that outlive their builders, voyages measured in centuries. Here the enemy is not impact but endurance. Systems drift, materials age, institutions fracture, and a single error can echo for generations. A plan can survive a launch and still fail quietly in the long middle. Even contact without travel carries its own loneliness. Light is fast, yet across interstellar distances it is also late. So late that a conversation becomes archaeology. A signal can arrive after its sender has changed, collapsed, or moved on, and the silence between replies can be longer than civilizations last. Of course, the mind reaches for exits, wormholes, warp drives, shortcuts through the fabric of space. We will treat those ideas with respect and with skepticism, tracing where general relativity invites them and where nature seems to demand a price we do not know how to pay. The question is not whether imagination is bold enough, but whether the universe permits the receipt. And beyond our galaxy, the stage itself is shifting. Space expands, horizons form, and the reachable universe may be smaller than the visible one. There are places we can see forever, yet never touch. Because geometry, not engines, decides the boundary. By the end, impossible will mean something precise and unsettling. Not a magical prohibition, but a practical sentence imposed by distance and time. One that could explain a crowded cosmos that still never visits. If that is true, the silence above us is not evidence of emptiness, but of separation. So we begin where the mystery is sharpest, with a universe that should be alive and a sky that refuses to answer. Not to chase fantasies, but to interrogate the laws. Because if aliens cannot reach Earth, it will not be for lack of desire. It will be because the universe, in its deepest rules, has built a cage that even intelligence cannot easily escape. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We will move from the silent sky to the tyranny of distance, then into relativity's speed limit and the brutal economics of near-light travel. And when every shortcut is tested, From generation ships to wormholes, we will confront the final question of what, if anything, can cross the cosmic cage. Look up at the Milky Way and you see a calm band of light, like a pale river poured across black velvet. On a clear night it feels ancient, steady, and close enough to touch. Yet, it is a structure 100,000 light-years wide, built from hundreds of billions of stars. In long exposure, that soft band resolves into granularity, into knots and lanes and bright cores. Dark dust cuts through it like smoke, hiding whole neighborhoods of suns. The glow is not a single thing, but the combined light of countless stars whose photons have traveled for years before reaching your eyes. Now set a second clock beside it, the clock of human history, and the contrast becomes almost cruel. Our species has used complex language for a blink of cosmic time, and our written records cover only a thin slice of that blink. Our radio signals have travelled for barely a century, forming a bubble of noise that is still small on a galactic map. Our first steps beyond Earth are still within 1 light second of home, and even our farthest probes remain inside the Sun's local territory. Voyager 1, launched in 1977, is only a fraction of a light day away, and it will need tens of thousands of years to approach another star. The distance is not philosophical, it is arithmetic. These two clocks barely overlap, and the mismatch is the first clue to the silence. The galaxy has had billions of years to produce intelligence, to iterate through experiments of chemistry and evolution. We have had barely enough time to notice the question, and barely enough time to build instruments that can even ask it. That question is usually asked as a taunt, as if the universe has failed a simple expectation. Where is everybody? If the universe is old and vast, and if life is not unique, then the sky should be crowded with evidence, with signals stacked on signals, with artifacts and traces. Enrico Fermi put it bluntly in the mid-20th century, during a lunch conversation that became legend. If they exist, and if they can travel, then they should be here. Yet the sky stays silent, and the silence has weight, because it persists across decades of listening. We have scanned for signals and found mostly noise, the hiss of the cosmos and the chatter of our own technology. Radio telescopes have swept across frequencies, looking for narrowband tones that nature rarely makes. We have mapped planets and found worlds everywhere, and the discovery has been so rapid that it has reshaped astronomy within a single generation. We have watched the stars and seen no clear engineering, no unmistakable beacons, no visitors crossing the sky with intent. There are no unambiguous megastructures blocking starlight in clean geometric signatures. There are no transmissions that repeat with the kind of precision that screams design. The paradox is not that we see nothing, because emptiness is always an option. The paradox is that statistics suggest we should see something, and still we do not. Between what seems probable and what is observed, a gap opens, and that gap becomes a story. This film does not begin by arguing that aliens are real. It begins by treating them as plausible, even likely, and then asking a harder question that changes the entire frame. Not where are they? Could they ever get here? That shift matters because it changes the suspect, and it changes what counts as evidence. The problem might not be biology or culture or choice, even though those factors matter. The problem might be the universe itself, and the rules that every civilization inherits. The Milky Way is not empty, even if the spaces between stars feel like void. It is a crowded city with streets made of vacuum and time, with spiral arms that sweep around the center like slow weather systems. If there are other minds, they may be trapped in their own neighborhoods, separated by laws that do not negotiate. To frame the scale, consider what a light year means, because the phrase hides its violence behind familiarity. It is not a unit of time. It is the distance light travels in a year, and light is the fastest thing we know, about 300,000 kilometers each second. That number is hard to hold in the mind, so we translate it into something tangible. A light year is nearly 10 trillion kilometers, a distance so large that our everyday sense of travel collapses. When we say the galaxy is 100,000 light-years wide, we are describing a span that defeats intuition. Even our nearest star system is more than 4 light-years away, and that is the best case. That is 4 years at light speed, and light speed is already the limit written into the fabric of space-time. Every probe we have launched would take tens of thousands of years to cross that gap, even if it never had to slow down. So the silence could be a simple outcome of geometry, not a cosmic conspiracy. The universe may be full of life and still unreachable, because the distances are not merely large. They are large in a way that turns travel into a commitment across centuries. The Drake equation was invented to organize this uncertainty, not to solve it. Frank Drake introduced it in 1961 as a way to structure a conversation, to separate what we know from what we guess. It multiplies factors we barely know, and it turns ignorance into a range that can be argued about. How many stars have planets? How many planets are habitable? How often does life begin? How often does intelligence appear? How long do civilizations last? Each term is a door into a different science, and each door opens onto its own fog. The equation is not a prophecy, and it is not a magic number generator. It is a reminder that the galaxy offers many rolls of the dice, and that even modest probabilities can produce large totals when the number of trials is enormous. When you have hundreds of billions of stars, rarity can still be common. Modern astronomy has strengthened the early terms, and it has done so with data rather than hope. Planets are common. Many stars host multiple worlds. Some planets sit in temperate zones where liquid water could exist, and we have detected atmospheres that hint at complex chemistry. The Kepler mission and the surveys that followed revealed that planetary systems are not exceptions. They are the default, and our solar system is just one arrangement among many. Rocky planets appear around small red dwarfs and sun-like stars alike, and some exist in orbits where starlight could warm their surfaces. If those pieces are widespread, then the remaining uncertainty shifts, and the question becomes sharper. The bottleneck may not be the birth of life. The bottleneck may be the ability to cross interstellar space, because distance punishes every plan and magnifies every weakness. Because even if there are thousands of civilizations, they do not automatically become travelers, and they do not automatically become visible. They must survive long enough to try, and survival is not guaranteed on any world. They must build machines that can endure, and endurance is a different kind of intelligence than invention. They must spend energy on a journey that may never pay back, and that cost is not just fuel. It is infrastructure, risk, and time is the one resource no technology can manufacture. A civilization may choose to explore in other ways, but even that choice is shaped by physics. At this point, the story usually turns to the Great Filter, because it offers an explanation with teeth. It is the idea that something, somewhere, prevents most life from becoming a galaxy-spanning presence. The filter could sit behind us, meaning we are rare, or it could sit ahead of us, meaning our future is fragile. The filter is often imagined as biological, and biology does have choke points. Maybe life rarely starts. Maybe complex cells are rare. Maybe intelligence is a fluke that appears once in a billion experiments and then vanishes. Or it is imagined as social, because societies can fail in ways that nature does not. Maybe technology destroys its makers. Maybe civilizations choose silence, hiding from unknown threats, or simply refusing to broadcast. Maybe they lose interest in expansion, turning inward to virtual worlds or local perfection. But there is another possibility that sits beneath all of these, quieter and harder to argue against. Physics itself may be the filter. Not physics as a single wall, but physics as a cage made of several bars, each one simple to state and brutal to overcome. Bar 1 is distance, and it is not just a number on a chart. Space is not a gap between places. It is the dominant feature of the universe, and it scales faster than our intuition, so that even nearby stars are separated by gulfs. Bar 2 is the speed limit, and it is not a rule we can bargain with. The universe has a maximum speed for information and matter, and it is not a suggestion. Relativity makes it a law that reshapes time, mass, and energy as you approach it. At high fractions of light speed, time dilates and momentum grows, and the engineering becomes strange. From the traveler's perspective, the journey can shorten, but from the outside world the clock keeps running. The universe allows no simple shortcut that preserves both speed and causality. Bar 3 is energy, because motion at interstellar speeds is expensive in the most literal sense. To push large objects to extreme speeds requires power on the scale of nations or stars. The numbers rise faster than the engineering optimism, because kinetic energy grows with the square of velocity. Even before relativity dominates, doubling your speed quadruples your energy cost, and the fuel problem becomes a trap. Carrying fuel means adding mass, and adding mass means needing more fuel, a spiral that rockets engineers have fought since the first launch. Advanced propulsion can change the curve, but it cannot erase the bill. Bar 4 is survival over time, and time is the hidden killer of interstellar dreams. Interstellar travel is not a trip. It is a multi-generation project, or a machine that must function for centuries, or a biology that can pause and restart without losing itself. A ship must endure micrometeoroids, radiation, thermal cycling, and the slow decay of materials. Electronics must resist cosmic rays that flip bits and degrade components. Life support, if it carries life, must be an ecosystem that stays stable without a planet beneath it. These barriers do not care how smart you are, and they do not reward confidence. They do not care how advanced your materials are. They do not care how determined your culture becomes, because they are not opponents with motives. A civilization can be brilliant and still be confined, the way an island culture can master the sea and still be limited by the horizon. It can be ancient and still be local, because longevity does not automatically produce mobility. It can be loud and still never be heard here, because loudness fades with distance. So the silence may not be evidence of emptiness. It may be evidence of separation, of minds scattered across a disk of stars who can never close the gap. The Milky Way could be teeming and still feel vacant because the streets between neighbourhoods are too long. This is the emotional pivot of the film, and it changes the colour of the night sky. The universe that should be crowded can still feel empty from where we stand, because our senses evolved for savannas and shorelines, not for parsecs. A galaxy full of minds can look like a dead sky when no one can cross the gulf. That idea is unsettling because it reframes our place in the cosmos, without offering comfort. We are not necessarily first. We may simply be isolated, living inside a bubble of light and time that keeps us from knowing what else is out there. It also reframes what contact would require, and why contact might be rare. Not a friendly message, not a curious ship, but a victory over constraints that have never been broken. If someone arrives, it means they solved problems that still defeat our best equations. If you want to reach Earth from another star, you must solve a chain of problems at once, and none of them can be skipped. You must accelerate, coast, and decelerate without running out of fuel, because arriving too fast is the same as not arriving. You must choose trajectories that aim at a moving target. You must shield against radiation and dust at high speed, because even a grain of sand becomes a bullet when velocities climb. You must keep systems stable for decades or millennia, and stability is not a single technology. It is redundancy, repair, and the ability to adapt when the unexpected happens. And you must do all of this while the universe keeps moving, because space is not a static stage. Stars orbit the galaxy, targets drift, the map changes while you travel, and the destination you launch toward is not the destination you will meet. Even communication is trapped by the same rules, and it carries its own kind of loneliness. A message from a civilization 1,000 light years away is 1,000 years old when it arrives. A conversation becomes archaeology, and every reply is a letter to descendants. That delay changes what we mean by contact, and it raises an awkward question. Are we listening for a living voice, or for a fossil signal that outlived its makers? When we point antennas at the sky, we are not just scanning space, we are scanning time. So when we ask why no one has visited, we are also asking what kind of project a visit would be, and who would authorize it. It would be the most expensive journey imaginable, aimed at a planet that might change before you arrive. Oceans shift, climates swing, species rise and fall, and civilizations can vanish. This is why the documentary's central question is not a debate about belief, because belief does not move spacecraft. It is a test of possibility, grounded in numbers and constraints. Do the fundamental laws of physics make reaching Earth effectively impossible, even for minds far older than ours? The hook is simple and sharp, and it refuses to soften. If the universe is full of minds, why has the sky stayed silent? Are we alone, or simply unreachable? Separated not by choice but by the geometry of space-time? To answer, we will not start with speculation about motives. We will start with measurement, because measurement is the one language that does not care what we want to be true. We will take the 4 barriers one by one, and we will treat them as engineering constraints, not metaphors. We will ask what distances demand, and how navigation works when your road is empty space. We will ask what the speed limit permits, and what relativity does to travellers and to observers. We will ask what energy budgets allow and what propulsion concepts can realistically deliver. We will ask what survival over time requires and what it means to keep a mission alive longer than any human institution. Some solutions will sound familiar, like generation ships and suspended animation, because we have imagined them for a century. Some will sound exotic, like wormholes and warp drives, because imagination keeps pushing against the bars. Each will be tested against what physics actually says, not what stories prefer. We will keep returning to the same uncomfortable possibility, because it is the simplest explanation that still fits the facts. The universe may allow intelligence to arise often, and still prevent it from ever meeting. The silence above us might be the sound of countless civilizations hitting the same walls, each one brilliant, each one trapped. Or it might be the sound of a universe where travel is so hard that no one tries, because the cost is too high and the payoff too distant. Either way, the first prison bar is the simplest to understand, and it sets the scale for everything that follows. Before we argue about speed, energy, or survival, we have to face the raw scale, the plain distance between stars. We begin where every interstellar story begins. We begin with distance, and with how far space really is. Distance is the first prison bar because it is built into space-time itself and it does not negotiate. In Chapter 1, we asked why the sky stays silent, and we promised to start with measurement. Here the measurement is simple, and the implications are brutal. A light year is a distance, not a feeling, and not a poetic way to say very far. It is how far light travels in 1 year in vacuum, about 946 trillion kilometers, or 5.88 trillion miles. But it also acts like a time delay, because nothing outruns light, and causality rides with it. Space bakes latency into reality, and every gap becomes a waiting period you cannot pay to remove. That dual meaning matters, because it changes what near means in a universe with finite signal speed. When a star is 4 light years away, it is also 4 years away in information, even before you move an inch. Any signal you send arrives years later, and any reply arrives years after that, assuming someone is listening. A conversation becomes a slow exchange between different versions of history, each message arriving like a postcard from the past. This is why interstellar space is not just big, like a larger ocean or a longer road. It is big in a way that forces time into every plan, and time is a cost that compounds. Even if propulsion were perfect, you still cannot remove the delay, because the delay is not mechanical. The universe makes distance and time the same obstacle, welded together by the speed of light. Start with the nearest plausible destination, because nearest is the kindest case the cosmos offers. Proxima Centauri is about 4.24 light-years away, a small red dwarf in the Alpha Centauri system. It is the closest star to the Sun, and it is still outside every human travel instinct. On a star map it looks adjacent, yet it sits beyond a gulf that swallows generations. At light speed it is a 4-year sprint, but light speed is not a vehicle speed, and it is not a casual engineering target. Light is massless, and it does not need to carry fuel, shielding, or a computer that must keep working. The phrase "at light speed" is a reference line, not a promise, and it exists to show how harsh the baseline already is. At more realistic extremes, the numbers stretch until they stop feeling like missions and start feeling like eras. At 10% of light speed, a probe needs roughly 42 years just to arrive, and that is only the cruise time. That ignores acceleration and deceleration, which can add years unless you accept a violent start and a blind flyby. It ignores detours, failures, and the slow attrition of hardware that must endure without a rescue. Imagine the visuals in real time: Earth shrinking to a bright dot, the Sun becoming just another star, and then the long black interval where nothing seems to happen. The camera holds on a spacecraft coasting through darkness, while the calendar pages turn in silent stacks. In interstellar travel, most of the story is not the launch or the arrival. Most of the story is the waiting. TRAPPIST-1 sits at about 39 light-years, and it became famous because it hosts multiple rocky worlds packed close to a small star. Some of those worlds orbit in a temperate range, where liquid water is not instantly impossible, at least by temperature alone. At light speed it is still a 39-year trip, and at 10% it becomes nearly 4 centuries. The target is not far in the way oceans are far, because oceans do not demand centuries, and they do not demand machines that outlive nations. Now widen the map to the Milky Way itself, because even a single galaxy is an empire of distance. The galactic centre is about 26,000 light-years from Earth, and that is not the edge. That is the middle, where stars crowd more densely and orbits tighten around a supermassive black hole. If a civilization lived near that centre, its nearest neighbours might still be thousands of light-years away, separated by a silence that is purely geometric. The galaxy is a disk tens of thousands of light-years wide, with stars spread through a thin thickness like dust in a beam of light. We live in one spiral arm, not in a central hub, and not in a region where travel lines naturally converge. The geometry alone turns the Milky Way into scattered neighbourhoods with enormous empty streets. A crowded city can still be unreachable if the roads are measured in light, and if every intersection charges years. Historically, our first attempts to grasp these scales were acts of careful triangulation, not imagination. Astronomers measured stellar parallax, tiny shifts in a star's position as Earth moves around the Sun, and used that angle to infer distance. The angles were so small that early instruments strained to see them, and for centuries the stars remained effectively at infinity. When the first reliable parallax measurements arrived in the 19th century, they did not make the universe feel closer. They made it feel suddenly, mathematically vast. To make the scale visceral, shrink the solar system to a model, because models are how the mind survives numbers. Let the Earth, Sun distance be one astronomical unit, 1 AU, the baseline of our local map. In that scale, the nearest star is about 268,000 AU away. The number is not poetic, it is a ratio that destroys intuition, because it says the solar system is a speck in a field. Picture a clean graphic, Earth and Sun a single step apart on a tabletop. Then a long hallway of empty floor stretching to a dot that almost disappears. You can label the dot Proxima, but the label is doing most of the work. The emptiness between the marks is the real content, and it is what space actually is. Most of the universe is not objects. Most of the universe is separation. That ratio explains why our probes are still local, even when they feel heroic. Voyager 1 is not even a light day away, despite decades of travel and despite leaving the planets behind. Its radio signal takes on the order of a day to reach Earth, depending on its exact distance, which is already enough to make control feel sluggish. It is leaving the Sun's influence, not approaching another star, and the gap between stars is not a gap we have started to cross. Distance also changes what exploration means, because it changes the relationship between action and feedback. In the solar system, you can send a craft and still expect updates within minutes to hours, and you can correct mistakes while they are still mistakes. Across light years, updates arrive years later, and control becomes prediction rather than steering. You do not fly the ship, you launch a plan and wait, hoping your assumptions survive contact with reality. That waiting is not just psychological, it is operational, and it reshapes engineering from the start. If a system fails, you may not know for years, and the failure may have cascaded into other failures by the time you learn. If you discover a navigation error, you may discover it after the correction window is gone, when the required burn is no longer small. Interstellar missions are not interactive, they are pre-committed like arrows that cannot be called back. This is where emptiness becomes a physical obstacle, because interstellar space looks like nothing, but it is not nothing. It contains sparse gas, magnetic fields, and dust grains, all moving relative to you. At low speed, those particles are mostly harmless, and they drift past like a thin fog. At high speed, they become impacts, and impacts become the dominant design constraint. A single dust grain at relativistic velocity carries enormous kinetic energy, because energy scales with the square of speed, and then climbs even faster as relativity tightens its grip. The ship does not meet a gentle vacuum, it meets a stream of microscopic bullets. Shielding becomes a mass problem, and mass becomes an energy problem, because every kilogram you add must be accelerated and protected. Distance forces you to carry protection for a long time, and it forces you to trust that protection without maintenance. Even the gas matters when speed climbs, and the interstellar medium stops being background scenery. Hydrogen atoms are thinly spread, sometimes only a few per cubic centimetre, which sounds like nothing compared to air. But over light years you plough through vast columns of them, and the totals become enormous. At high velocity, each atom is a radiation event, a tiny collision that can ionize surfaces and generate secondary particles. the interstellar medium turns into a continuous abrasion of particles and energy, like driving through invisible sand at a speed that makes sand explosive. The visuals here are deceptive because the camera sees blackness while physics sees impacts. A hull that looks pristine in a distant shot is, at the microscopic level, being peppered and heated. Over decades, that peppering becomes wear, and wear becomes failure. Radiation is also part of the road, and it does not care that you are far from any planet. Cosmic rays, high-energy protons and heavier nuclei, strike electronics and materials, sometimes punching through like tiny cannonballs. Solar storms fade with distance, but the galaxy supplies its own background of energetic particles. Over decades, small damage accumulates into failures, and the failure may be a flipped bit that becomes a wrong decision. A long journey is not one hazard, it is millions of small hazards that add up, and that is what makes it feel unfair. You can design for a single shock, but you must also design for the slow rain of shocks. The ship becomes a statistical object, living in probability rather than certainty. The longer the time, the more the improbable becomes inevitable. Navigation sounds easy until you quantify it, because point at the star and go is not a real instruction. Stars move and the sun moves and the galaxy rotates, so the target is not fixed in space. Your destination is drifting on its own orbit, and its motion is not a footnote. You must aim for where it will be, not where it was when you launched, and that requires models that remain accurate for decades. Course correction is also unforgiving over long baselines, because small angles become huge distances. A tiny angular error at launch becomes a vast miss after years of coasting, even if the craft performs exactly as commanded. 1 arc-second of error can translate into billions of kilometers at interstellar distances, enough to miss an entire planetary system. The ship can pass through the target system's orbit and never come close, like an arrow that threads a needle's shadow. Even if you can see the target, measurement has limits that do not vanish with better intentions. Sensors have noise, star catalogues have uncertainties, and onboard clocks drift as components age and temperatures cycle. Every estimate is a probability distribution, not a perfect coordinate, and the distribution has tails. Over decades, those distributions widen unless you constantly correct, and constant correction is not free. Correction requires propulsion, and propulsion requires propellant or power, which must be carried or generated. If you plan frequent corrections, you must budget for them from the start, and that budget competes with shielding and instruments. If you plan few corrections, you accept larger risk, and risk is not abstract when the nearest help is years away. Distance forces a trade between fuel and accuracy, and it forces you to choose your failure mode early. There is also the problem of reference frames, which sounds academic until you are alone in deep space. In deep space, there are no landmarks, only distant stars and background radiation, and even those are seen through the lens of your motion. You navigate by timing, angles, and inertial measurement, and each of those systems can carry subtle bias. Any bias becomes a slow, persistent drift, quiet at first, then decisive. Then there is the logistics problem, which distance turns into a statistical trap, because time is the enemy of reliability. A spacecraft is a collection of parts with finite lifetimes, each with its own failure curve and weak points. Over long durations, the chance that something breaks approaches certainty, even if the chance per day is tiny. Reliability becomes a numbers game, not a confidence game, and the numbers do not flatter optimism. In human terms, we already see this in satellites and probes, and we see it even when they are close. Components fail, software glitches, sensors degrade, and unexpected interactions appear between systems that looked fine on the ground. Those failures are manageable when the craft is nearby, and sometimes manageable when it is in the outer solar system with careful planning. Over light years, management becomes impossible in real time, and improvisation becomes a myth. So an interstellar mission must carry redundancy, and redundancy is never weightless. It must carry spares, repair tools, and self-diagnosis, and it must be able to reconfigure itself when parts die. Every layer of redundancy adds mass and complexity adds new failure modes, because more parts mean more ways to fail. The craft becomes a compromise between robustness and brittleness, balanced on engineering judgment. If the mission carries life, the logistics multiply again, and the word supply changes meaning. Life support is not a tank of air, it is a closed ecosystem or a continuous recycling machine that must run without pause. Oxygen must be regenerated, Water must be purified, carbon dioxide must be scrubbed, and nutrients must cycle without poisoning the loop. Over decades, small imbalances become crises, and crises become fatal if no outside resupply exists. The ship becomes a moving biosphere that must remain stable without Earth, and stability is harder than it sounds. Microbes evolve, systems drift, and tiny leaks become major losses when time is long. Even psychology becomes operational, because a crew is not a payload, it is a living system that can fracture. Distance turns every human weakness into an engineering parameter. Even if the travelers are machines, time still attacks, and it attacks in ordinary ways that add up. Lubricants degrade, seals crack, radiation damages semiconductors, and micrometeoroids pit surfaces until coatings fail. Thermal cycling stresses joints, and vacuum can cause materials to outgaze and change properties. You cannot assume a device works after a century just because it worked on day one, because the century is the test. The tyranny of distance also changes the meaning of rescue, and it does so with cold arithmetic. In the solar system, rescue is hard but imaginable, because travel times are measured in months and signals in hours. Across light years, rescue is a second interstellar mission, launched years after the first, with its own risks and its own delays. By the time help arrives, the original mission is either finished or lost, and the word rescue becomes ceremonial. This pushes designs toward autonomy, because autonomy is what remains when conversation is impossible. The craft must make decisions without waiting for Earth, and it must do so with incomplete information. It must detect hazards, choose corrections, and handle failures alone, sometimes rewriting its own plans. Autonomy is not optional when the round-trip light time is measured in years, and when the environment punishes hesitation. Distance also punishes communication itself, because physics dilutes your voice as it travels. Signals spread out, weakening with the square of distance, so doubling distance quarters the received power. To be heard across light years, you need high power, tight beams, and large antennas, and you need them to keep working for decades. Even then, the message arrives faint and late, buried in noise that must be patiently extracted. That lateness changes strategy, because it changes what it means to learn. If you discover something important near the destination, Earth learns years later, when budgets and governments may have changed. If Earth sends new instructions, they arrive years after conditions have changed and after the craft has already acted. Distance turns command into archaeology, and response into delayed interpretation, like reading a conversation where every line is out of date. Now place this back into the central question of the film, because the silence is not only a mystery, it is a measurement. If the universe is full of minds, why has the sky stayed silent, even as our instruments sharpen? One answer is that silence is what distance looks like, and distance is what it enforces. Civilizations can exist, broadcast and build, yet never overlap in time and reach, like ships passing in separate oceans. Even a fast ship does not erase the time gap, it only reduces it, and reduction is not the same as removal. Even a powerful transmitter does not erase the delay, it only increases detectability, and detectability is not contact. The universe enforces separation through geometry and finite speed, and it does so impartially. Distance is not a challenge you solve once, it is a tax you pay everywhere, and the interest rate is time. It is tempting to say that advanced technology makes distance irrelevant, because our history is full of shrinking worlds. Sailing ships became steamships, then aircraft, and continents became neighborhoods within a lifetime. But distance scales every requirement, and scaling is where plans break, because the margins disappear. Double the distance and you double exposure to dust, radiation, and failures, and you double the time that every system must remain honest. Multiply distance by 10, and you multiply the mission's vulnerability to everything that can go wrong, including the rare events. A 1 in a million strike is not comforting when you face millions of opportunities for it to happen. A tiny software flaw is not minor when it has decades to express itself. Distance turns low probabilities into scheduled appointments. This is why nearby becomes a cosmic illusion, a word that survives only because we need it. Proxima is nearby only because everything else is worse, and because it is the least impossible star. TRAPPIST-1 is nearby only because the galaxy is enormous, and because our imagination wants a reachable cluster of worlds. The galactic center is nearby only because the universe beyond the Milky Way is larger still, and because our minds resist the next step outward. Distance also hides in our language, and language is how we smuggle danger past ourselves. We say 4 light years, and our minds hear a small number, as if it were a short drive. But the unit is a warning, because it is built from the fastest thing in nature, and it still needs years. If light needs years, then anything slower needs lifetimes, and lifetimes are not a rounding error. So far we have treated distance as the main barrier, and it already looks close to fatal, even before we talk about engines. Yet distance alone would not be fatal if speed were unlimited, because you could turn years into hours by brute motion. If you could cross 4 light years in a day, you could treat the galaxy like a navigable ocean, and the silence would demand a different explanation. The fact that we cannot do that is not a cultural limitation, it is a physical one. But the universe does not offer unlimited speed, and it does not offer loopholes for convenience. It offers a hard limit that ties motion to energy, and energy to mass and time to causality, and those links tighten as you accelerate. To understand why interstellar travel collapses from difficult to effectively impossible, we have to meet that limit directly without metaphor. We have to look at what happens as you chase light, and why the chase becomes punishing. We leave the map of distances and step into the rule that governs them. We meet the universe's speed limit, and the strange physics that appears as you approach it. Distance set the scale, but speed decides whether scale can ever be paid down. If the universe is full of minds, why has the sky stayed silent? Are we alone, or simply unreachable? Chapter 2 showed that light years are also years of delay, welded by physics. Now we meet the rule that makes that weld permanent, even for the best imaginable engine. In the dark between stars where nothing seems to resist motion, the real resistance is geometry. Einstein's special relativity begins with an uncomfortable postulate. The speed of light in vacuum is invariant for all inertial observers, regardless of their motion. It does not matter whether you chase the beam or flee from it. Every careful measurement returns the same number. This is not a local speed limit like a sign on a road. It is built into spacetime's geometry, shaping how time and distance are measured. In that geometry, c is less like a velocity and more like a conversion factor, binding meters to seconds in the fabric of reality. The invariance is forced by experiments, not by taste. Maxwell's equations predict a wave speed, and nature refuses to let different observers disagree. In the late 19th century, physicists expected an ether wind to shift light's measured speed. Yet the Michelson-Morley interferometer found no drift at all. That null result was eerie in its simplicity, and it demanded a new accounting of motion. Lorentz and Poincaré built mathematical scaffolding to preserve Maxwell's equations, and Einstein stripped the scaffolding into a principle. If the laws of physics are the same in all inertial frames, then light speed cannot be negotiable. To keep light speed fixed, the universe adjusts everything else. Time intervals and spatial lengths become frame-dependent, while the laws stay consistent. The adjustment is not a trick of instruments, but a redefinition of what simultaneous even means. Relativity is often introduced as a set of weird effects. In this story, it is a lock, because the effects intensify exactly where travel needs relief. The closer you push towards C, the more the lock tightens, smoothly at first, then with a sudden merciless steepness. Define the Lorentz factor gamma because it controls the whole escalation. Gamma equals 1 over the square root of 1 minus v squared over c squared. It looks harmless on a page, but it is a lever that turns ordinary speeds into extraordinary costs. At low speeds, gamma is almost 1, so Newton works well. As v approaches c, gamma rises without bound, and intuition fails. The curve is gentle near the origin, then it bends upward until it feels like a cliff. Time dilation follows directly from gamma. Moving clocks tick slower compared with clocks at rest in a chosen frame. This is not philosophy. Muons created in Earth's upper atmosphere survive longer when they move fast, and atomic clocks on aircraft return measurably out of sync. Length contraction follows as well. Distances along the direction of motion shrink in the moving frame, again by factors tied to gamma. In the ship's own coordinate grid, the star ahead is not dragged closer by magic, but by the way spacetime parcels out distance when you change frames. These are not illusions or mechanical slowdowns. They are how spacetime preserves the same light speed for every observer. If time did not stretch and lengths did not compress, different observers would compute different light speeds, and Maxwell's waves would become frame-dependent. The traveller's perspective sounds like a gift, and it is a real effect. If you ride a fast ship, your proper time between departure and arrival can be reduced. Inside the cabin, heartbeats and computer cycles remain normal, yet the universe outside seems to hurry. That reduction is the seed of a popular myth. People hear time dilation and conclude that relativity makes interstellar travel easy. The myth is seductive because it is partly true, just not true in the way the story needs. The myth hides a frame switch. The traveller experiences less time, but the departure world still measures a long interval passing. The ship's crew may feel they have stolen time, yet the homeworld pays the full calendar cost. If Earth is 4 light-years away, Earth's geography does not move closer for Earth. Earth still waits years, because Earth's clocks do not borrow time from the ship. The radio silence between departure and arrival still spans years of unanswered transmissions. Relativity does not erase distance for everyone at once. It trades time and distance between frames, and the trade cannot satisfy both sides. You can compress the trip in the traveller's diary, or compress it in the map of the outside world, but not both simultaneously. A ship at high speed can see the distance to the target contracted, but that contraction is paired with the outside world's time dilation, keeping causality consistent. In the ship's frame, the destination is closer, and in the Earth frame, the ship's clock runs slow. 2 accounts that reconcile only when you respect the transformation. So the central question sharpens rather than softens. Even if travellers can shorten their own experience, can any civilization pay the energy bill to reach such speeds? The universe offers a bargain, but it demands payment in the only currency that scales without mercy. Relativistic momentum is the next turn of the key. Momentum becomes gamma times m times v, so pushing harder yields less speed gain. The same thrust produces diminishing returns, because more and more of your effort goes into increasing gamma rather than increasing v. In Newtonian space, acceleration adds velocity linearly. In relativistic space, each increment of speed costs more momentum than the last. You can keep accelerating forever in your own proper time, yet your speed relative to the departure frame asymptotically approaches c. Energy tightens the trap even more. Total energy becomes gamma times mc squared, so kinetic energy grows as gamma minus 1 times mc squared. That formula is compact, but it hides a brutal implication. Rest energy is already enormous, and relativistic kinetic energy quickly becomes comparable. As v approaches c, gamma approaches infinity. That means the required energy to reach c diverges, no matter how clever the engine. The wall is not made of steel or plasma, it is made of a denominator that goes to 0. This is the wall, stated cleanly. No object with rest mass can be accelerated to light speed using any finite amount of energy. You can approach the limit, but the limit recedes as you spend, like a horizon that retreats with every step. Light can travel at sea because light is massless. A ship is not massless, and its mass is not a detail you can engineer away. Even if you build with perfect materials, even if you eliminate every unnecessary gram, the remaining rest mass anchors you to the subluminal side of the light cone. Sometimes people say the ship's mass increases with speed. Modern language prefers that rest mass stays constant, while energy and momentum rise. Either phrasing points to the same operational reality, because what matters is how much harder it becomes to change the ship's motion. The faster you go, the harder it becomes to accelerate, and the harder it becomes to stop. Stopping matters because arrival is not a flyby. A visitor must decelerate into the destination system, and deceleration costs energy like acceleration. Relativity therefore doubles the pain. You pay to get fast, and you pay again to shed that speed, unless you accept a one-pass ghost visit. A probe that screams through a system at relativistic speed is not exploration, it is a blink. Too brief to map, too fast to turn. The numbers become brutal long before c. At 0.1 c, gamma is barely above 1, but the kinetic energy is already enormous for macroscopic mass. In visual terms, the ship is carrying a planet-scale lightning bolt in its velocity alone. At 0.2 c, the energy quadruples compared with 0.1 c in the classical approximation. The ship's required energy climbs faster than mission planners expect. The curve punishes linear thinking, because the first tenth of c is not 1/10 of the challenge. At 0.5 c, gamma is about 1.15, and the kinetic energy is a large fraction of the ship's rest energy. That is not a fuel tank problem, it is a civilization-scale power problem. you're no longer asking for a better engine, but for a new relationship with energy production. At 0.9 C, gamma is about 2.29, and the kinetic energy exceeds the ship's rest energy. At 0.99 C, gamma is about 7.09, and the bill explodes. Each additional 9 after the decimal is not a refinement, but a new tier of impossibility. This is why light speed is not a challenge like climbing a taller mountain. It is a curve that turns vertical, making the last steps infinitely expensive. The wall is mathematical, yet it behaves like a physical barrier, smooth to the touch until you try to cross. A common response is to invoke advanced propulsion. Better engines can improve efficiency, but they cannot change the gamma divergence. Even a perfect engine, converting stored energy to kinetic energy with no losses, still faces the same asymptote. Efficiency changes how much stored energy becomes motion. It does not change how much motion costs near C. The price is set by space-time itself, and space-time does not negotiate. Even before relativity dominates, propulsion faces the rocket equation. If you carry reaction mass, you must accelerate your fuel, which demands more fuel. The tyranny is recursive, fuel to push fuel, until payload becomes a shrinking island in a sea of propellant. Relativity makes the rocket equation harsher at high exhaust velocities. The mass ratio required for extreme delta V becomes absurd for any macroscopic payload. In practice, even optimistic fusion rockets run into exponential scaling long before they approach the relativistic regime. Beamed sails and external power try to dodge that trap. They move the energy source off the ship, but the energy requirement remains. The sail becomes a bright, fragile target, an artificial comet tail catching photons instead of dust. A laser array can push a light sail without onboard propellant, yet the array must deliver staggering power for long durations, and it must aim with extreme precision. Over interstellar distances, even microradian pointing errors bloom into misses measured in millions of kilometers. The ship still must survive impacts and radiation at high speed. Energy is not the only bill, but it is the bill that scales fastest. As the bow of the craft cuts through sparse interstellar gas, the gas does not feel sparse anymore. Relativity concentrates it into a forward storm. This is where the documentary's tone turns from hard to eerie. The universe is not merely large, it's guarded by math that grows teeth. The stars look inviting, but the space between them is patrolled by invariants and asymptotes. Time dilation is real, and it is not a free ticket. It helps the traveller's clock, but it does not help the universe's geography and the departure frame. The homeworld still measures the ship's journey as a long absence, with all the social and political consequences that implies. If a civilization sends a crew at 0.99 C to a star 100 light-years away, the crew might experience a much shorter trip. Earth still waits roughly a century. The night sky over the launch site will change, and constellations will slowly shear, while the crew's memories remain fresh. That gap matters for the central question. Visitors may arrive having aged little, but the sending civilization must persist across the outside time. What institutions can hold a plan steady for generations, and what cultures can keep faith with a mission they will never see return? A mission is not just a ship and a crew. It is a long chain of support, decision-making and continuity that must survive while the ship is gone. Even the language of the launch may drift, turning mission logs into artifacts that require translation. Relativity therefore shifts the burden rather than removing it. It can spare the travellers, but it cannot spare the civilization that launches them. The ship becomes a time capsule moving through space, while the society behind it becomes a river that cannot stop flowing. Another misconception hides in the phrase near light speed. People imagine that 0.9 C is close enough to treat C as reachable. But the wall is not at 1.0 C only. The cost curve steepens so sharply that each extra 9 in the decimal demands disproportionate energy. That is why the practical ceiling matters. Even 0.1 C or 0.2 C is already beyond plausible propulsion for large payloads with known physics. The problem is not only generating energy, but storing it, directing it, and surviving the consequences of releasing it as thrust. To see why, translate speed into energy per kilogram. At 0.1 C, kinetic energy is about 4.5 times 10 to the 14 joules per kilogram. That is roughly the energy released by tens of thousands of tons of TNT per kilogram of ship, and it is only the outbound leg. Multiply by millions of kilograms, then add deceleration. The arithmetic becomes a kind of horror, because it scales with mass whether you like it or not. Accrued habitat, shielding, supplies, and redundancy all add kilograms, and kilograms become joules. At 0.2 C, the per kilogram energy is about 4 times larger. The scaling does not care about optimism, and it does not care about need. At those energies, a propulsion failure is not an accident. It is an explosion written in advance. A civilization might harvest stellar power, build vast collectors, and still face the logistics of delivering that energy as directed thrust. Power is not the same as controllable propulsion. You must shape energy into momentum change, and you must do it without destroying the machine that channels it. Then there is waste heat, because no system is perfectly efficient. Any inefficiency becomes heat that must be radiated away, and radiation is slow in vacuum. In deep space there is no air to carry heat off, only infrared photons leaking away from glowing surfaces. At high power, thermal management becomes a limiting constraint. The ship and the beaming infrastructure must dump heat without melting themselves. Radiators grow large, and large structures are hard to accelerate, and that loops back into the energy bill again. Relativity also changes the environment the ship plows through. Interstellar dust and gas become a forward beam of energetic impacts in the ship's frame. What looks like a thin mist from Earth becomes, to the ship, a head-on rain of particles whose kinetic energy has been amplified by speed. At 0.1 C, a grain of dust can carry the energy of a bullet. At higher fractions, impacts become radiation events that erode and ionize surfaces. The front of the ship becomes a sacrificial face, and every added layer of shielding is another mass penalty that must be paid twice. Shielding adds mass, and mass adds energy cost. The wall is not one barrier, it is a stack of coupled penalties. When you push one constraint down, another rises. Propulsion, heat, shielding, and structural limits tightening together like gears. So far we have treated C as a speed limit for matter. But the deeper reason it is a wall is that it protects causality. Causality is the order of cause and effect, the rule that prevents tomorrow from rewriting yesterday. Special relativity ties causality to the light cone structure of spacetime. Light cones divide events into what can influence what. If you stay at or below C, signals remain inside the cone, and cause precedes effect in every frame. Visually, a world line that stays inside the cone is a promise. It says that information moves forward, that consequences follow actions, and that physics can be predictive rather than self-contradictory. The cone is not drawn in the sky, yet it governs every possible exchange. Faster than light travel breaks that structure. If a signal can outrun light, there exist frames where the signal arrives before it is sent. This is not a philosophical trick. It is a direct consequence of relativity's frame transformations, which mix space and time between observers. With FTL, simultaneity becomes a weapon. Two observers moving relative to each other can disagree on the time order of space-like separated events. In ordinary life, that disagreement is harmless, but with superluminal signals, it becomes a lever that can flip after into before. Combine FTL with ordinary relative motion, and you can build a tachyonic anti-telephone. A message is sent, received, and replied to in a way that reaches the sender's past. The paradox is not an edge case. It appears as soon as you allow controllable FTL in a relativistic universe. Once messages can go to the past, paradoxes appear immediately. You can warn yourself not to send the message, and the logic collapses. Prediction becomes impossible, because the future would have the power to edit the conditions that created it. Physics responds by treating FTL as more than an engineering problem. It threatens the consistency of the laws, because inconsistent causality destroys prediction. A universe that cannot preserve cause and effect cannot preserve science, and it cannot preserve stable histories. General relativity adds more nuance, but the danger remains. Many spacetimes that allow effective FTL also allow closed time-like curves, paths that loop back in time. In those geometries, a traveller could in principle return to an earlier event on their own world line, and the story becomes circular. Wormholes, warp metrics, and other shortcuts are often proposed as loopholes. In many analyses, they require exotic energy conditions, and they flirt with causality violations. Even when equations permit a formal solution, stability becomes the next barrier, because small disturbances can grow until the shortcut collapses. Quantum effects may destabilize would-be time machines, and chronology protection is a serious conjecture. The idea is not that time travel is merely difficult, but that the universe may enforce a kind of self-consistency by making the required conditions physically unattainable. The key narrative point is simple. The speed limit is not only about reaching destinations, it is about keeping reality ordered. When we ask whether aliens can reach Earth, we're not only asking about engines, we're asking whether the universe allows any method to outrun its own causal structure. This is why C feels like a wall rather than a challenge. A wall is not something you push harder against, because the wall holds up the building. The building, in this case, is the logical order of events that makes a coherent universe possible. Relativity also explains why the silence can persist even in a crowded galaxy. Civilizations can exist and still be separated by a limit that cannot be cheated without breaking time. The Milky Way could be full of lights, each one trapped in its own bubble of reachable space. If they travel slowly, the distances take centuries or millennia, and missions become fragile. If they travel fast, the energy cost becomes astronomical, and the environment becomes lethal. If they imagine FTL, they collide with causality, and the problem stops being engineering. The universe seems to defend its own timeline. That defense is quiet, mathematical, and universal. There is no border patrol, only invariance that every experiment confirms. The silence above us may be less a mystery of life and more a consequence of the rules that let life have a consistent past. This is the relativity loophole myth in its final form. Time dilation can make the trip feel short for the crew, but it cannot make the trip short for everyone. Earth still waits, and the sending world still waits. The galaxy still rotates, civilizations still rise and fall, and the calendar still turns in the rest frame. A visitor could arrive to find that the world they aimed for has changed beyond recognition. That is not a failure of planning, it is a consequence of long outside time. The speed limit therefore locks distance into place. It does not matter how advanced a civilization becomes, because the cost curve is written into space-time. We can approach C, but the closer we get, the more each increment costs. The lock tightens exactly where the temptation is strongest. This chapter leaves us with a constrained hope. If we cannot beat C, maybe we can approach it and accept the trade-offs. But approaching it is not a simple matter of better materials. The energy costs turn the key in the lock, and the lock clicks harder with every fraction of C. Next, we follow that click into the accounting. We move from speed to the deeper constraint that speed invokes: energy, fuel, and the brutal arithmetic of propulsion. Relativity set the wall at light speed, but energy sets the slope long before it becomes a wall. If the universe is full of minds, why has the sky stayed silent? Are we alone, or simply unreachable by any sane budget? Speed is not just a number on a dial, or a thrill that scales smoothly with courage. Speed is stored violence because kinetic energy must be paid up front, carried safely through years of exposure, and then paid again to stop. Start with a simple conversion that refuses to stay simple once you push it hard. For a mass m moving at velocity v, relativistic kinetic energy is gamma minus 1 mc squared. Gamma is the Lorentz factor, 1 over the square root of 1 minus v squared over c squared, and it is the quiet function that turns ambition into arithmetic. At low v, gamma is near 1, and Newton's 1/2 mv squared works well enough. Past about 0.1 c, the approximation stays close in percentage terms, yet the absolute energy already becomes staggering. The numbers are not merely large, they are large in the way that reorganizes what a vehicle even means. Per kilogram, 0.1 c costs about 4.5 times 10 to the 14 joules of kinetic energy. That is not fuel in a tank, it is a planetary scale budget embedded in motion. On screen, you can picture it as a single kilogram carrying the energy of a strategic arsenal, except it is perfectly silent until something forces it to stop. Scale that to a modest probe of 100 tons, and the kinetic energy reaches about 4.5 times 10 to the 19 joules. That is comparable to years of output from a large power grid, concentrated into one moving object no larger than a bus. In a dark frame, the probe looks small and harmless, yet its momentum is a kind of compressed history. Then remember, the trip is not one burn and not one number. A mission that wants to arrive and do anything must decelerate, so the energy requirement roughly doubles before inefficiencies. If you want to enter orbit, land, maneuver, or even point instruments steadily, you must buy control with more energy. At 0.2 c, the energy rises by about 4 times in the classical regime, and the curve still looks gentle on paper. Yet the bill grows faster than the engineering intuition, because intuition is trained on cars and aircraft, not on fractions of light speed. Even at 0.2 C, a speck of mass becomes a moving power plant's lifetime output. At 0.5 C, gamma climbs to about 1.15, and kinetic energy becomes a large fraction of rest energy. The ship begins to resemble a moving energy reservoir that must never fail, because failure is not a breakdown, it is an explosion in slow motion. Visually, the craft can be shown as a bright vector slicing through darkness, its danger invisible, its cost hidden in the math. At 0.9 C, gamma is about 2.29, and the kinetic energy exceeds the rest energy. Each added 9 after the decimal is not progress, it is a new order of expense. The last few percent towards C are not a finish line, they are a cliff where the slope steepens into near vertical cost. This is the first punchline of the energy abyss. The universe does not forbid acceleration. It makes it ruinously expensive at the scales interstellar travel demands. Physics is not a policeman here. It is an accountant who never misses a decimal. Now translate energy into propulsion, because energy alone does not move a ship in a chosen direction. Momentum change requires throwing something backward or pushing against an external field, and both have hard accounting. In the background, imagine a ledger filling with numbers as the ship's velocity ticks upward. For rockets, the accounting is the Tsiolkovsky rocket equation, written down in the early 20th century as rocketry became more than fireworks. Delta V equals exhaust velocity times the natural log of initial mass over final mass. It is a compact equation with a brutal personality. That logarithm hides the trap because it makes the problem feel tame until you ask for too much. To gain more delta V, you do not add fuel linearly, you multiply fuel exponentially, because the fuel must accelerate itself. Each extra increment of speed demands not just more propellant, but propellant to push the propellant you just added. Every kilogram of propellant must be pushed along with the payload, the tanks, the engines, and the structure. That means you carry propellant to carry propellant until payload becomes a rounding error. In a visual diagram, the payload shrinks while the fuel stack grows like a tower that never stops rising. Even before relativity, the rocket equation punishes ambition with a kind of cold elegance. Interstellar delta V pushes designs into mass ratios that are physically buildable only on paper, because real tanks have thickness, real engines have turbopumps, and real structures buckle. The equation assumes ideal staging and perfect burns, and reality subtracts from that ideal at every seam. Chemical rockets illustrate the limit cleanly, because they are the best understood and the most forgiving. Chemical exhaust velocities are a few kilometers per second, and even heroic staging cannot reach meaningful fractions of C. The fastest chemical exhaust is still slow compared to the speed you're trying to buy. To reach 0.1 C with chemical exhaust would require mass ratios so large they exceed the mass of planets. Chemical propulsion is not hard for interstellar travel, it is irrelevant. It is the wrong tool in the way a bicycle is the wrong tool for crossing an ocean. Nuclear thermal rockets improve exhaust velocity, but not by enough to change the story's shape. They might reach tens of kilometers per second, which helps within the solar system, yet barely touches interstellar requirements. The physics of heating propellant runs into material limits, because no solid wall can sit forever next to a miniature sun. Electric propulsion can reach higher exhaust velocity, but it trades thrust for time in a way that becomes punishing. Low thrust means long acceleration arcs, and interstellar timelines still demand enormous total energy. If you accelerate for years, you also expose the spacecraft to years of wear, micrometeoroids, and the slow drift of tiny failures. So the story shifts from fuel chemistry to energy density, because the bottleneck is deeper than engine type. Interstellar travel is an energy storage problem first, and a thrust problem second. The ship is less a vehicle and more a container for concentrated work. Compare energy sources by specific energy, the energy per kilogram of fuel, and the hierarchy becomes obvious. Chemical reactions deliver around 10 to the 7 joules per kilogram, which is impressive for everyday machines. But it is microscopic compared to what near-light motion demands. Nuclear fission delivers around 10 to the 14 joules per kilogram in principle, because splitting heavy nuclei releases binding energy. Fusion can approach several times 10 to the 14 joules per kilogram depending on reaction and efficiency, because light nuclei fall into a deeper binding energy well. These are not small upgrades, they are jumps across 7 orders of magnitude. Antimatter annihilation reaches about 9 times 10 to the 16 joules per kilogram of matter alone. It is the ceiling set by E equals mc squared, and it looks like salvation. In a clean animation, matter and antimatter meet and vanish into a burst of light. Simple, perfect, and misleading. Yet specific energy is not the whole story, and it never was. A rocket must also carry reaction mass, and it must convert energy into exhaust momentum with finite efficiency. Even if you have infinite energy, you still need a way to throw momentum backward without destroying your engine. High energy density does not automatically mean high exhaust velocity, because exhaust velocity depends on how you channel energy into propellant. You must choose propellant, nozzle physics, and containment, and each choice adds mass and failure modes. The more extreme the energy source, the more the engineering becomes a battle against your own power. Fission rockets face a second barrier besides energy density, and it is the tyranny of hardware. Reactors are heavy, shielding is heavy, and high-temperature materials limit how fast you can throw propellant. The reactor must also remain stable under acceleration and vibration, because a cracked fuel element is not a minor defect. Fission also produces intense radiation and waste heat, which do not politely disappear. That heat must be rejected, and rejection in vacuum demands large radiators that add mass and fragility. The spacecraft begins to sprout thin panels like black wings, delicate, essential, and vulnerable. Fusion seems like the next rung, because stars do it naturally and make it look effortless. But stars use gravity and enormous confinement, and a ship must do it with machinery that survives vibration and time. On Earth, we have spent decades chasing controlled fusion, and the difficulty is not a lack of desire. Project Daedalus is the canonical example of optimistic fusion staging, born from the 1970s era of bold engineering studies. It proposed inertial confinement micropellets and a multi-stage vehicle to reach about 0.1 C. The concept is visually striking, a drumbeat of tiny explosions, each one a controlled starlet pushing a magnetic nozzle. Daedalus reached that speed only by becoming mostly fuel, because the rocket equation does not negotiate. The payload fraction was tiny, the structure was immense, and the mission accepted a flyby because braking was too costly. In narrative terms, it is a triumph that still admits defeat at the destination. Icarus and later studies refine the idea, but the core tension remains, and it remains for physical reasons. Ignition, pellet fabrication, magnetic nozzles, and erosion at high power remain uncertain at required scale. Even if the physics works, the engineering must work millions of times in a row without a single catastrophic misfire. Fusion also inherits the rocket equation in full, even when the exhaust velocity is high. Even with high exhaust velocity, the mass ratio for accelerate and decelerate missions becomes punishing, especially for heavy shielding and redundancy. The moment you add safety, you add mass, and mass is what the equation punishes most. Then there is antimatter, the seductive extreme that turns every spreadsheet optimistic at first glance. In pure energy density, nothing beats it, and the math suggests near-relativistic missions with manageable mass. It is the rare concept that looks better as you push towards C, until you ask how to build it. But antimatter is not a fuel you mine from a convenient asteroid. It must be manufactured, and manufacturing it is an energy sink with terrible efficiency in any known process. Particle accelerators can make antiparticles, yet most of the input energy becomes heat and secondary radiation, not stored antimatter. To make antimatter, you spend far more energy than you get back, because production yields are low. A civilization must accept massive losses just to stockpile grams. Imagine the industrial footprint implied by a kilogram. Power stations, cooling loops, and years of continuous operation devoted to a single fragile inventory. Storage is the next wall, and it is a wall made of ordinary matter. Antimatter cannot touch normal matter, so it must be held in electromagnetic traps, isolated from vibration, dust, and the ship's own outgassing. Even a stray molecule becomes a bullet when it meets its opposite. Traps require power and stability for years, and any containment failure is catastrophic. Scaling from nanograms in laboratories to kilograms in spacecraft is a leap across engineering chasms. In a visual sequence, the containment field flickers for an instant and the scene cuts before the inevitable flash. Even if containment works, antimatter propulsion creates intense radiation that does not care about elegance. Annihilation products include gamma rays and pions, which are hard to collimate and harder to shield. If you cannot aim the energy, you cannot turn it into thrust efficiently, and inefficiency becomes lethal heat. Shielding against that radiation adds mass, which raises energy needs, which demands more antimatter. The loop tightens until the theoretical advantage erodes in practical design. The ship becomes a compromise sculpture, thick where it must be thick, fragile where it cannot afford thickness. So rockets, even exotic ones, face a shared penalty that does not soften with optimism. Carrying your own reaction mass makes high delta V exponentially expensive, and the exponent does not care about civilization level. A richer civilization can build bigger, but bigger is not the same as easy. That pushes attention to a different class of ideas, the ones that try to cheat the mass ratio. If you cannot carry the fuel, you try to leave it behind and push the ship with external power. The ship becomes the projectile and the engine becomes infrastructure. Beamed propulsion does exactly that, and it has been discussed in serious form since the laser became more than a laboratory curiosity. A laser or microwave array stays at home, and a sail or receiver rides the beam, turning photons into momentum. The sail is not pushed by wind, but by the pressure of light itself. The rocket equation relaxes because the ship does not haul propellant, and that is a real victory. But the energy bill does not vanish. It moves to the infrastructure that must deliver power across distance. You're still paying the same physics, only now you pay it with stations, mirrors, and grids. Photon momentum is small, so the required power is enormous for any meaningful mass. To accelerate a meaningful mass to a meaningful fraction of c, you need beams measured in terawatts to petawatts. In imagery, the beam is a rigid, invisible column, and the sail is a bright disk trembling at its tip. Those beams must stay locked on a sail for minutes, hours, or days, depending on acceleration and mission design. The pointing precision must be extreme, because tiny angular errors miss the sail entirely. A miss is not a small loss of efficiency, it is the end of acceleration and the start of drift. Diffraction sets another limit, and it is set by wave optics rather than engineering bravado. A finite aperture produces a spreading beam, so long-range beaming demands arrays with kilometre to thousands of kilometres scale, depending on wavelength. The array becomes a landscape feature, a geometric scar etched into a planet or a solar orbit. The sail must also survive the beam, and survival is not guaranteed at these intensities. High-intensity risks melting, tearing, and charging, and the sail must remain stable without tumbling while it is being pushed. Even slight wrinkles can turn a smooth push into a chaotic spin. Beamed sails also face the arrival problem, which returns like a debt collector at the destination. The home array can accelerate you, but it cannot easily decelerate you at the destination unless a second array already exists there. Without braking, the mission becomes a flyby, a brief glance paid for with decades of preparation. Some concepts use magnetic sails or interstellar medium braking, trying to turn the sparse gas between stars into a brake pad. Those ideas trade propellant for huge structures and long braking distances, and they still struggle at high speed. The faster you go, the harder it is to grab the thin mist of the interstellar medium. So even the fuel off-ship option has a price tag that looks like planetary engineering. It demands industrial scale, long-term coordination, and a willingness to spend energy as a signal flare. If anyone is doing this, their launches would be among the brightest artificial events in their system. Now bring in the constraint that every high-power system tries to hide behind optimistic efficiency numbers. No engine is perfectly efficient, and inefficiency becomes waste heat that must go somewhere. In practice, even a few % loss at petawatt scale becomes a furnace you must carry. In space, heat leaves only by radiation, because there is no air to convect it away. Radiated power scales with area times temperature to the fourth, so dumping gigawatts requires either huge radiators or dangerously high temperatures. The Stefan-Boltzmann law is simple, and it is merciless. Huge radiators mean mass and surface area means vulnerability to impacts and fatigue. Radiators are thin by necessity, and thin structures hate impacts, vibration, and long-term degradation. A pinhole leak or a torn panel is not cosmetic when it is your only way to stay cool. High temperatures reduce radiator area, but raise material limits and infrared signature at the same time. A near-light ship becomes a bright beacon, glowing with the heat of its own power system. Even if it tries to hide, thermodynamics forces it to announce itself in the infrared. Waste heat is not a side issue, it is a design dictator that shapes everything downstream. If you cannot reject heat, you cannot run the engine, and if you cannot run the engine, you cannot pay the speed bill. The radiator is not an accessory, it is the other half of the propulsion system. The same applies to the beaming infrastructure, which must also live in the real universe. A laser array that outputs petawatts must also manage waste heat from generation, conversion, and optics, likely at continental scale. The array's cooling systems could rival the complexity of a city's water and power networks. At this point, the chapter's tension tightens around a single idea that is easy to say and hard to accept. Interstellar travel is not blocked by a no from physics, it is priced by physics until only extremes remain. The galaxy is open in principle, yet closed in practice by the cost of doing business. A civilization could, in principle, harvest stellar output with swarms of collectors, building a partial Dyson-like shell of mirrors and panels. It could store energy, build arrays, and dedicate generations to a single launch window. In that scenario, the spacecraft is the final step of a much larger industrial ritual. But the cost is not just energy. It is opportunity cost and risk that cannot be diversified away. The stored energy of a near-light craft is also a weapon, and any failure is a disaster on launch scales. A society that can build such a craft must also decide it can live with what that craft could do by accident. A ship carrying relativistic kinetic energy cannot crash gently, and it cannot be captured by a planet like a slow probe. If guidance fails near a planet, the impact is an extinction-level event delivered at interstellar velocity. Even a near miss could scour an atmosphere with radiation and debris. This reframes the silence in the sky, because the problem is not only technical. Visitors are not just rare because travel is hard, but because travel is dangerous to the sender and the receiver. Would you launch a civilization-scale projectile into a populated galaxy if you could not guarantee its path for centuries? Even a probe is a liability when it carries civilization-scale energy, and liability changes behavior. A cautious civilization may decide that launching such projectiles into the galaxy is ethically and strategically unacceptable. Silence can be a policy, not a lack of imagination. And even if they accept the risk, the engineering must survive long burns and long coasts in an environment that never forgives. High power stresses materials, erodes nozzles, and amplifies tiny faults into mission-ending cascades. A cracked weld, a misaligned magnetic field, or a drifting control loop can end everything far from help. So the energy abyss has layers, and each layer is a different kind of impossibility. First you must generate the energy, then store it, then convert it into momentum, then reject the waste heat, then survive the consequences. Each step is individually hard, and together they become a coupled system that resists simplification. The deeper you go, the more the constraints couple together, and coupling is where designs die. More shielding means more mass means more energy means more heat, and more heat means more radiator mass. The spiral is not rhetorical, it is the algebra of engineering reality. This coupling is why optimistic spreadsheets collapse into impossible machines once you add structure and safety. The numbers do not merely add, they multiply, and every solution inflates another part of the system. The vehicle becomes a moving compromise balanced on the edge of its own margins. Return to the central question with the accounting now visible, and the mystery sharpens. If the universe is full of minds, reaching Earth requires not just desire, but a willingness to spend like a planet. It also requires a willingness to accept that the journey itself is a continuous hazard. A near-light mission is not a ship in the usual sense, with cabins and romance and a sense of scale. It is an energy project with a payload attached, and the payload is the smallest part of the story. The payload may be cameras, sensors, or minds, but the bulk is always the machinery of speed. The universe allows you to accelerate, but it charges you in the only currency that cannot be faked. It charges energy, and it charges it with compounding interest. The closer you get to C, the more every decision becomes a decision about power. This is where the chapter pivots forward, because the price tag is only the first barrier. Suppose a civilization somehow pays the bill and launches anyway, accepting the heat, the mass ratios, and the infrastructure. Suppose the sail holds, the pellets ignite, the traps stay stable, and the guidance remains flawless. At those speeds, space itself stops being empty, and the darkness becomes crowded with consequences. The interstellar medium becomes a firing range, and every atom ahead becomes a particle impact with catastrophic energy. A single hydrogen atom at 0.9 C carries the punch of a high-energy particle accelerator experiment, and the ship meets them by the trillions. The next barrier is not how to go fast, because the math already told us what fast costs. The next barrier is how to survive going fast when the universe turns the void into a shooting gallery. And that is where the silence may deepen, because even paid for speed does not guarantee safe passage. If the universe is full of minds, why has the sky stayed silent? Are we alone, or simply unreachable? Chapter 4 priced the launch, and the numbers were already civilization scale, with energy budgets that look like national grids. Now assume someone pays anyway, because the next barrier is not cost. The next barrier is contact with the medium between stars, because at relativistic speed, emptiness becomes a weapon. Interstellar space is not a perfect vacuum. It is a thin fog of gas and dust spread across light years. In telescope images it looks like nothing, yet spectrographs and radio maps reveal a structured medium. At walking speed that fog is nothing, and at orbital speed it is manageable. At 0.1 C and beyond, every particle carries kinetic energy that scales with v squared, then climbs with gamma. The equation is simple, but the intuition is not. When velocity rises, energy does not just increase, it concentrates into smaller times and smaller impact zones. The ship is not merely fast, it is compressing years of random collisions into a continuous forward assault. Start with dust, because dust is mass concentrated into grains. Typical interstellar grains can be micrometers across, with densities like silicates, carbon or icy composites. Under a microscope they are jagged and irregular, more like shattered glass than smooth spheres. A micrometer grain sounds harmless, until you multiply its mass by 1/10 of light speed. At 0.1 C, the grain's kinetic energy lands like an explosive impact on a tiny area. The damage is not a neat hole, it is a crater, a shockwave, and a spray of fragments. In high-speed lab shots, material behaves less like a solid and more like a fluid for microseconds. The front surface pits, then roughens, then becomes a better target for the next hit. This is the bullet problem in its simplest form. You're not dodging asteroids, you are being shot by sand. The grains are rare, but the path is long, and long paths turn rare events into near certainties. Over several light years, even low-number densities integrate into a grim tally. Even when the grain is smaller, the physics stays ugly. A nanogram at 0.1 C still carries energy comparable to a rifle round, delivered in a flash. The pressure spike can exceed the strength of metals by orders of magnitude. The ship's nose becomes a sacrificial shield, and the shield must survive not one strike, but millions. Impacts do not only remove material, they change it. Shock heating melts and vaporizes the local surface, then recondenses it into brittle layers with trapped voids. The microstructure is rewritten, grains refine, phases separate, and residual stresses accumulate. Repeated strikes drive microcracks, delamination, and fatigue that no lab test fully reproduces. Then comes spallation, the hidden multiplier. A high-speed impact launches secondary fragments from both the projectile and the shield, like shrapnel from a microscopic bomb. Those fragments become their own micrometeoroids, ricocheting inside cavities and striking deeper layers. A single hit can seed a cascade of internal damage that spreads beyond the initial crater. Secondary showers also include radiation. When fast particles slam into nuclei, they can produce neutrons, gamma rays, and energetic ions. These are not gentle byproducts, they are penetrating messengers of nuclear interactions. A shield that stops a grain can still create a radiation burst behind it, inside the habitat's line of sight. Now add the most common projectile of all, hydrogen. The interstellar medium is mostly hydrogen atoms and protons, spread thinly across light years, mixed with helium and trace heavier ions. In calm space they are a background, a faint plasma that barely touches a drifting probe. At low speeds they are a drag term, and at high speeds they become a particle beam. In the ship's frame, the forward direction compresses the flux. Relativity concentrates incoming particles into a narrower cone ahead and increases their energy through blue shift. The ship is not moving through a calm mist, it is facing a headwind that hardens into radiation. The geometry changes too. What was isotropic becomes directional, like driving into sleet at highway speed. At modest gamma, each hydrogen atom hits like an energetic ion. At higher gamma, the energies approach accelerator regimes, and the front of the ship becomes a target in a continuous experiment. This is not metaphorical physics, it is the same regime used to probe materials in particle labs. The heating is not just thermal, it is ionization and lattice damage. The forward-facing surface charges, sputters and erodes. Atoms are knocked out of the material, and the surface slowly boils away without ever melting. This is sputtering in the literal sense. Momentum transfer ejects atoms one by one. Over decades and centuries, this is sandblasting by single atoms. The crew does not need to be struck directly to be harmed. Secondary particles penetrate, scatter and deposit dose in tissue and electronics. A few centimeters of structure can stop some components, yet neutrons and gammas are indifferent to thin walls. Radiation becomes a system-wide reliability problem, not a localized puncture problem. Cosmic rays were already there before the ship launched. The galaxy is filled with high-energy particles from supernova remnants, pulsars and shock fronts that accelerate nuclei to extreme energies. We learned this the hard way, from balloon experiments and early satellites that saw detectors light up above Earth's atmosphere. A stationary habitat can shield and manage dose, but an interstellar mission stretches exposure across long durations. Long duration turns baseline into cumulative risk. DNA damage accumulates, cancer risk rises, and the immune system degrades under chronic exposure. Cells can repair some breaks, yet repair is imperfect, and errors compound quietly over time. Electronics suffer single-event upsets, latch-ups, and long-term displacement damage. Relativistic travel makes cosmic rays worse in a specific direction. In the ship's frame, forward-arriving radiation is blue-shifted, and its apparent intensity increases. The crew sees an anisotropic sky, with a brighter, harder radiation field ahead. Even the psychological effect matters. Danger is no longer everywhere, it is concentrated like a spotlight. Even photons become part of the hazard. Starlight and background radiation are Doppler shifted forward, moving energy into higher frequencies. What was infrared can slide toward visible and beyond, adding to heating and material stress. The forward view can become a compressed glare, dim stars bunching and brightening into a small patch of sky. Solar events add another layer when the ship is near a star. Coronal mass ejections and solar energetic particles can spike dose dramatically, overwhelming normal shielding assumptions for hours or days. Space agencies already plan storm shelters for crews near Earth, and those are short missions by comparison. A ship cannot schedule its entire trajectory around stellar weather, especially across multiple systems. The central question tightens here, because physics is not just limiting speed. Physics is turning speed into exposure, and exposure into failure. A civilization can pay the energy bill once, but it must pay the survival bill every second. The void is not a distance problem alone, it is a continuous environment problem. So designers reach for shielding, and shielding looks like the obvious answer. Put enough mass in front and the bullets stop. But shielding is a trap because mass is what Chapter 4 already punished. Every kilogram is a promise you must accelerate, steer, and eventually slow down again. Passive shielding scales with aerial density. To stop particles you need thickness, and to stop secondary radiation you need more thickness. In practice you also need coverage. No gaps, no seams, no fragile edges. Every added kilogram must be accelerated and decelerated, doubling the energy burden. A thick monolithic shield also creates its own secondaries. High energy ions striking heavy nuclei produce cascades that can increase dose behind the shield. The paradox is unsettling. More armor can sometimes make the interior radiation spectrum worse. Sometimes lighter materials, like hydrogen-rich plastics, reduce secondaries but require more volume. There is history behind these trade-offs. Early nuclear engineers learned that gamma shielding favors dense materials, while neutron shielding favors hydrogen-rich ones. Spacecraft designers inherited those lessons, then discovered that the cosmic ray spectrum does not respect simple categories. A practical shield becomes a layered compromise, tuned to many threats at once. Whipple shields offer a partial compromise. A thin bumper layer shatters an incoming grain, spreading its energy before it reaches a rear wall. The gap matters because it turns one crater into a cloud that can be absorbed. In orbital debris protection, this approach is proven, and it has saved real spacecraft. But Whipple's shields are tuned to certain speeds and particle sizes. At relativistic velocity, the impact physics changes toward plasma formation and nuclear interactions. The shield becomes less like armour and more like a target that must manage an explosion. The debris cloud can also be so energetic that it behaves like a cutting torch. Layering helps, but layering multiplies complexity. Each layer must be aligned, supported and maintained for decades, despite vibration, thermal cycling and gradual creep. Each layer is also another surface that can erode, charge and shed debris into the ship's own path. The ship starts to resemble a nested set of compromises, each one buying time at a price. Some proposals turn to electromagnetic shielding. If the hazard is charged particles, then fields might deflect them. A magnetic bubble could in principle steer protons around the hull, reducing direct hits. In concept art it looks elegant, a luminous bow wave of invisible force. Yet fields do not stop neutral dust grains. Many grains are weakly charged, and charge can fluctuate with radiation and plasma interactions. A strong field also demands power, superconductors, and stability under constant bombardment. If the field collapses even briefly, the ship takes the full flux at the worst possible moment. Electrostatic concepts face similar limits. High voltages attract electrons and ions, and arcing becomes a risk in plasma. The system must survive micrometeoroid punctures and still hold potential without catastrophic discharge. At high fields, even tiny imperfections can trigger breakdown. Nature finds the weakest point. Active defences sound like science fiction, but they are the next rung people reach for. Detect a grain ahead, then vaporise or deflect it with a laser or particle beam. In principle, it is elegant because you avoid carrying thick armour. In practice, it becomes a race between photons, computers and geometry. The detection problem is the killer. A micrometer grain is dark, cold and tiny against the background. It reflects little light, emits little heat, and occupies almost no pixels until it is too late. At near-sea closing speeds, the time between detection and impact can be milliseconds or less. Reaction time is not only computation, it is physics. Your sensor must gather enough photons or returns to confirm a target, and confirmation takes integration time. Your weapon must deliver enough energy at enough distance to matter. At these speeds, enough distance is not comforting. It vanishes rapidly. Even if you see the grain, you must hit it precisely. Beam divergence, pointing jitter, and dust's uncertain trajectory all work against you. The smallest angular error becomes meters of miss at long range. A miss is not a small error, it is an impact at relativistic speed. There's also a cruel irony in preemptive vaporization. If you turn a grain into plasma too close to the ship, you still take the momentum and much of the energy. You trade one projectile for a shotgun blast of ions and X-rays. The problem is not only stopping mass, it is managing what that mass becomes. Some designs propose a forward dust cloud as a sacrificial buffer, release particles ahead, and let incoming grains collide with the cloud first. The ship rides behind its own artificial mist, hoping to soften the worst impacts. Visually it is haunting, a craft chasing its own faint halo through the dark. But a buffer cloud must be replenished, guided, and kept ahead at the same speed. Replenishment means carrying mass, and carrying mass returns to the energy abyss. Guidance means control systems that must never fail. If the cloud disperses, the ship suddenly faces the raw medium again, so the ship's front becomes a consumable. It must be designed for erosion, replacement and redundancy, like a heat shield that never stops re-entering. The mission becomes not a single vehicle, but a travelling factory of spare parts. Somewhere inside, machines must mine stock, print structures, and verify integrity without human hands. Maintenance is not a side plot, it is the plot. Over a century, seals age, lubricants degrade, and polymers embrittle as radiation breaks molecular chains. Thermal cycling pumps joints and fasteners, slowly changing tolerances. Over multiple centuries, even metals creep, electronics corrode, and microscopic defects grow into cracks. Erosion makes maintenance constant. Every impact removes atoms, and every removal changes surface geometry. The leading edge slowly loses its designed shape, and shape matters for field, sensors, and heat flow. Antennas, sensors, radiators, and optics are all exposed, and exposure is cumulative. Radiators are especially vulnerable. They must be thin to radiate efficiently, and thin structures hate impacts. A ship that needs high power also needs large radiator area, and large area is a larger target. Even small punctures can change fluid loops, cause leaks, and force rerouting. This loops back to Chapter 4's coupling. More shielding means more mass, which means more energy, which means more heat. More heat means more radiators, which means more vulnerable area, which means more damage. The design spirals into a tight corner where every fix creates a new surface to defend. Even if you accept heavy shielding, you still face the forward cone problem. At high gamma, the hazard is concentrated ahead, so the shield must be thickest where it is most needed. That makes the craft asymmetric, and asymmetry complicates structure and control. The vehicle becomes a hammerhead, mass forward, life tucked behind. The ship also becomes its own radiation source. Impacts create showers that scatter inside the hull, and scattering is messy. Propulsion systems, reactors, and power electronics add their own emissions. The interior becomes an engineered cave, where every wall is both protection and a potential generator of secondaries. A crewed ship must protect biology, which is fragile. A robotic ship must protect computation, which is also fragile in different ways. Memory bits flip, sensors drift, and redundancy slowly erodes as parts age out. Either way, reliability becomes the real payload. This is the grim truth of the interstellar minefield. The faster you go, the deadlier the medium becomes. Speed is not only expensive, speed weaponizes the void. The stars do not need defenses, the space between them is already armed. So the tempting response is to slow down. If you travel at a few thousand kilometers per second, dust impacts soften, and radiation blue shift relaxes. The ship can carry less armor, and active defenses become less absurd. The forward sky becomes less like a blowtorch and more like weather, but slowing down reopens the other prison bar. Time stretches, and the mission becomes centuries long in the departure frame. The civilization must sustain purpose, funding, and continuity across generations. What happens when the people who launched the ship are long gone, and only the ship remembers why it was built? And the ship must survive being a machine for centuries. Components drift out of tolerance, software rots, and stored materials outgas and degrade. Cold welding can seize mechanisms while radiation darkens optics and weakens insulation. Even perfect planning cannot fully predict 100 years of micro-failures. A slow ship also faces a different kind of hazard. It spends more total time under cosmic rays, more time accumulating dose, and more time letting rare failures occur. Lower intensity per second can still become lethal when multiplied by centuries. The mission trades sharp impacts for slow corrosion. This is where the chapter pivots toward the next enemy. If you cannot go fast without being shredded, you accept slow travel and try to outlast it. Then the ship itself becomes the adversary, because time attacks every system from the inside. The enemy is no longer a grain of dust, it is the calendar. The silence in the sky can come from this double bind. Go fast and the universe shoots you. Go slow and the universe waits you out. How many civilizations reach this point, do the math, and decide that the attempt is not heroic but irrational? The central question remains, sharpened by a new kind of isolation. The laws that let stars shine also fill space with dust, radiation, and relentless entropy. If there are minds out there, reaching Earth may be less about finding us, and more about surviving the path. Perhaps the quiet is not emptiness at all, but caution. Next, we assume the cautious choice. Suppose they slow down and accept centuries, because speed is too lethal. Then the story becomes about endurance, autonomy, and the slow sabotage of time itself. If the universe is full of minds, why has the sky stayed silent? Are we alone, or simply unreachable? The stars look close in a clear night, yet every bright point is a distance that punishes impatience. We listen for a reply, and the reply never comes, because the timescales are not human. Chapter 5 ended with a concession that feels like surrender. Go fast and the void becomes gunfire. Go slow, and time becomes the weapon. Between those two choices, the dream of crossing interstellar space becomes less a voyage and more a test of what a society can endure. Generation ships are the slow solution, and they are old in the imagination. Long before rockets, writers pictured arcs moving through darkness, lit by artificial suns and ruled by inherited duty. They accept that light years are also lifetimes, and they try to turn a vehicle into a lineage. This is not a ship in the usual sense, where you depart, travel and arrive within one biography. It is a closed civilization built to survive isolation longer than its founders can live. In the visuals, it is less a sleek craft than a moving habitat. Corridors like streets, farms like parks, and machinery like weather. The central question shifts without changing. Physics may allow slow travel, yet biology and sociology may still forbid arrival. The engines can be modest, but the mission must be absolute because there is no rescue ship behind you. Start with the simplest requirement, which is also the most unforgiving. A generation ship must carry an ecosystem, because resupply is not a plan. Between stars there are no ports, no spare air, and no second chance hidden in the dark. Air must be recycled with near-perfect closure, and that phrase hides a mountain of chemistry. Oxygen production, carbon dioxide removal, trace contaminants, and microbial balance must remain stable for centuries. A real habitat breathes through scrubbers, catalysts, membranes, and living plants, each stage with its own failure modes. Carbon dioxide is not merely a number on a sensor. It changes blood pH, cognition, and sleep. And small chronic elevations can erode performance long before they become lethal. Trace gases matter too: ammonia, formaldehyde, sulfur compounds, because closed spaces turn minor leaks into persistent exposure. Water must be recovered from every breath and waste stream, and that recovery must be obsessive. Condensers pull moisture from air, filters strip pathogens, and distillation or reverse osmosis polishes the result back to drinkable clarity. Losses that look trivial per day become fatal when multiplied by 1,000 years. In a sealed habitat, even a slow seep through a valve becomes a countdown. A few grams lost to a bad gasket is nothing on Earth, where rivers forgive you. In interstellar space, the same leak is a quiet theft from every future generation. Nutrients must loop through plants, microbes, and stored reserves, because food is not just calories. Soil chemistry, nitrogen fixation, and micronutrient drift cannot be allowed to wander. A crop can look healthy while slowly depleting selenium, iodine, or iron, until a population becomes sick in ways no one expects. The nitrogen cycle is especially delicate. On Earth it is stabilized by oceans, lightning, and vast microbial ecologies, but a ship has only what it brought. If nitrifying bacteria crash, ammonia rises, plants fail, and the ecosystem collapses from the bottom up. Closed systems do not fail loudly at first. They fail by slow bias, where tiny errors accumulate until the habitat crosses a tipping point. The most dangerous problems are the ones that resemble normal variation, because they invite delay. A filter that removes 99.9% of a toxin sounds excellent. Over centuries, the remaining fraction becomes the dominant story. The arithmetic is simple, and the consequences are not, because chronic low doses can alter fertility, immunity, and development long before anyone notices. Biology adds its own surprises because life is not a static component. Microbes evolve quickly, and a sealed habitat is a perfect arena for selection pressure. The ship becomes a laboratory that never closes, where every antibiotic, cleaning agent, and dietary shift nudges evolution in a new direction. Pathogens do not need malice. They only need opportunity, and long voyages create endless opportunities for mutation and spread. A cough in a corridor is not a local event because the air is shared by everyone, and the population is a closed network. Even benign organisms can become problems when the environment is stable and the competitors are few. Algae blooms, fungal spores, and biofilms can clog systems that were once clean. The visuals here are intimate and unsettling. Green films in pipes, slow mats on filters, and the quiet creep of life into every seam. So life support becomes governance of chemistry and evolution. The ship must constantly measure, correct, and anticipate its own living machinery. Sensors are not optional decorations. They are the ship's senses, and blindness is fatal. Then comes population genetics, the quiet constraint that turns romance into arithmetic. A small founding population carries a small library of variation. Over generations, random chance alone can erase alleles, and what is lost may be exactly what you need against a future disease. Minimum viable population is not one number, because it depends on fertility, lifespan, disease load, and social structure. But it is never tiny, and it is never comfortable. Conservation biology offers a warning from Earth. Small isolated groups drift toward fragility, even when they start healthy. Inbreeding depression is not theory, and it is not a moral judgment. It is the predictable result of limited mates, where harmful recessive traits surface and accumulate. The effect can appear as lower fertility, higher infant mortality, immune weakness, and a slow increase in congenital disorders. To avoid it, the ship needs either many people or stored genetic diversity. That means embryos, gametes, or sophisticated reproductive planning. It also means record keeping that survives politics, because genealogy becomes infrastructure. Stored genetics sounds like a shortcut, until you price its reliability. Cryogenic storage must survive power interruptions, radiation damage, and mechanical failure for centuries. Even if temperature holds, DNA is not immortal. Background radiation and chemical decay slowly nick and scramble the code. The storage system also has a social shadow: who controls access and who decides when to use it. A bank of embryos is a promise of future options, but it is also a lever of power. Even with stored diversity, demographics can shock the system. A pandemic, accident, or conflict can remove a cohort and collapse the breeding pool. The loss is not just numbers, but missing skills, missing caregivers, and missing continuity. A ship also needs age balance, and the balance is dynamic. Too many elderly means high medical load and reduced labour capacity. Too many children means high resource demand and social volatility, because youth is energy that must be fed and guided. So reproduction becomes policy, and policy becomes identity. Identity becomes conflict, because bodies become part of the mission's infrastructure. The ship must decide whether it is a family, a state, or a project, then live with the consequences. Now move from biology to machines, because machines must last longer than any warranty. A generation ship is a reliability experiment stretched across millennia. In the visuals, the camera lingers on bearings as seals and conduits, because the mundane parts are the true protagonists. Engineers often model failure with rates per hour, and the numbers look small on a spreadsheet. Over long durations, even tiny rates compound into near certainty. A 1 in a million event becomes likely when you roll the dice for centuries. Redundancy helps, but redundancy also ages in parallel. Two backups do not mean safety if both share the same design flaw. Common mode failures are the nightmare, one overlooked assumption that breaks every copy at once. Software is not immortal, and its fragility is subtle. Code depends on hardware, compilers, languages, and institutional memory, and all of those decay without constant renewal. A ship can lose the ability to rebuild its own tools, and the loss may look like a minor inconvenience until it becomes permanent. Radiation slowly flips bits and degrades sensors, turning data into noise. Mechanical parts wear, lubricants break down, and seals creep under thermal cycling. Even electronics that never move can fail as solder joints fatigue, and materials outgas or corrode. The ship cannot be maintained with a toolbox and a heroic attitude. It needs an industrial base that can fabricate parts, refine materials, and rebuild subsystems from raw stock. That implies mines, smelters, machining, and metrology, an entire economy inside a hull. That means machine tools, foundries, chemical plants, and quality control, all scaled to fit inside a travelling habitat. It also means training, documentation, and a culture that preserves technical competence. Without apprentices and standards, the ship becomes a museum of broken miracles. A ship that cannot manufacture is a ship that is already dying. Spares are finite and every repair consumes the future. The visuals shift from shiny components to worn workbenches, where a single cracked part can halt an entire subsystem. Resource economics becomes the hidden plot, because mass is destiny even at slow speed. Every kilogram launched is either living space, shielding, food buffer, or industrial capacity. Each choice is a trade, and the trade is permanent once the ship is underway. If you pack too many spares, you starve the habitat of volume and flexibility. If you pack too few, you guarantee a slow collapse. The ship must choose between redundancy and adaptability, and neither choice feels safe. Raw materials must be managed like a national reserve. Metals corrode, polymers embrittle, and composites delaminate, even when nobody touches them. Time attacks everything, especially the things you assumed would wait politely in storage. Energy continuity is the next hinge, because power is the ship's heartbeat. Without steady power, life support fails, manufacturing stops, and stored genetics warms into ruin. A brief blackout can become a generational catastrophe. A reactor can provide power, but it adds shielding, heat rejection, and long-term fuel management. Fuel must last, or be bred, or be recycled with extraordinary care. The reactor also becomes a political object, because whoever controls power controls survival. Solar power fades between stars and demands huge collectors. In interstellar space, the sunlight is a memory, and panels become vast, delicate wings. They must survive micrometeoroids and degradation, while still delivering enough energy to keep the habitat stable. Waste heat still must be radiated because thermodynamics never negotiates. Radiators must survive micrometeoroids for centuries, and leaks are not a maintenance inconvenience. A puncture is a slow fever, forcing the ship to shed capability to stay cool. So the ship becomes a coupled system again. More shielding means more mass, and more mass means more energy. More energy means more heat to reject, and more heat means larger radiators, each solution enlarging the next problem. The physics that priced near-light travel still echoes here. Slow travel reduces the bullet problem, but it does not erase thermodynamics. Even at modest speeds, the ship must pay the bills of entropy every day. Then there is radiation and health, because time is exposure. A slow ship spends centuries under cosmic rays, solar events, and secondary radiation from its own systems. Outside Earth's magnetosphere, the background is not dramatic, but it is relentless. Cosmic rays are not like ordinary radiation, and that distinction matters. They include heavy ions that punch through tissue, leaving dense tracks of damage that cells struggle to repair. Over decades, the risk accumulates as cancer, cataracts, and neurological effects that are difficult to predict. Shielding can reduce dose, but shielding is heavy, and heavy is expensive to accelerate and to rotate. Even at low speed, mass is still destiny. Designers may use water, polyethylene, or layered materials because hydrogen-rich shielding slows charged particles more effectively. Microgravity is another slow poison, and it is well documented in short missions. Bones thin, muscles waste, and cardiovascular systems adapt in ways that may not be reversible across generations. The danger is not just weakness, but developmental change, children growing into bodies shaped by a different constant. Rotation can provide artificial gravity, but rotation introduces engineering stress and complex structural dynamics over long time scales. The habitat becomes a spinning wheel, and the wheel must stay true. Bearings, trusses, and joints must endure continuous load without creeping into failure. A rotating habitat must keep balance, because imbalance becomes wobble. Mass shifts from farming, water storage, and construction can induce precession that stresses bearings and joints. Even daily routines, moving cargo, harvesting crops, can become part of the ship's attitude control problem. Motion sickness is not a footnote either. In a rotating world, the Coriolis effect can make simple movements disorienting, especially in smaller radii. The ship may need large dimensions to make gravity feel natural, and large dimensions demand more structure and more mass. Medical unknowns multiply with duration. Pregnancy, childhood development, and immune function under partial gravity are not well characterized even for decades. The ship must become its own medical research institution, because the data will not exist until it is created. A generation ship cannot run a short trial and then revise the plan. It must commit, then discover the consequences while already too far to turn back. That is the existential tension. Every experiment is performed on the only crew you have. Now the story turns psychological, because isolation is not an engineering parameter. It is a social environment with no exit. The camera finds a window, and beyond it there is only black, punctured by distant stars that never grow larger. A ship is a small world with a hard boundary. There is no frontier, no migration, and no external trade to relieve pressure. On Earth, societies vent stress through movement and exchange, but in a sealed habitat, every grievance stays inside. Conflict is not optional, it is a statistical certainty, and the only question is whether institutions can absorb it without breaking. Minor disputes can become existential when the stakes are air, water, and space. Governance must be stable yet adaptable, and that balance is rare even on Earth. Rules that work for launch may fail after a famine, a scandal, or a generational shift. The ship must evolve without losing coherence, which is a paradox written into its design. Authority will drift, because power always seeks permanence. Leaders will reinterpret the mission, and emergency powers will be claimed, then normalized, then inherited. Over centuries, a temporary measure becomes tradition, then becomes law. The mission also competes with daily life, and daily life always wins attention. People will care about love, status, art, and grievance more than a star they cannot see. A destination that exists only in lessons and diagrams is easy to doubt. Purpose decays when it is not reinforced by experience. The destination is an abstraction, and abstraction loses to immediate suffering. When a child is hungry or afraid, the promise of a future planet sounds like a story told to keep them obedient. Education becomes a survival system, not a luxury. The ship must teach not only skills but reasons, because reasons are the glue of compliance. Technical training must be paired with civic training, or else competence becomes a tool for rebellion. Language will change because language always changes when communities isolate. Symbols will shift and the founding story will be retold, simplified, and mythologized until it becomes religion or folklore. The mission patch becomes an icon, and the launch date becomes a holy day. That is cultural evolution under confinement. It is not a failure of character. It is what minds do when time is long and memory is fragile. The ship's culture will adapt to the ship because the ship is the only environment it knows. Mutiny risk is not cinematic. It is structural. If a cohort decides the mission is unjust, they can seize control of life support. They do not need weapons because a valve and a schedule can be more powerful than a gun. Even passive resistance is enough. Refuse maintenance, refuse reproduction policy, refuse rationing, and the ship's trajectory becomes irrelevant. The engines can keep burning, yet the society inside can decide to stop being a mission. Designers propose safeguards, and the proposals sound clean on paper. Lock critical systems behind automation, restrict access, or embed hard-coded constraints. Build a ship that cannot be commandeered, and you build a ship that cannot be fully lived in. But automation is built by people and maintained by people. A system that cannot be understood cannot be trusted, and distrust breeds sabotage. When a black box controls air and water, every malfunction becomes a conspiracy. The ship must therefore balance transparency with security. That balance is political, and politics is the one subsystem that cannot be debugged. You can patch software, but you cannot patch resentment. Time dilation does not save this, and that matters for the larger argument. It helps the travelers experience fewer years at high speed, but generation ships are explicitly slow. Their problem is not subjective time, but objective duration. From the departure world, the mission becomes a legend long before it arrives. Messages may still be sent for a while, but institutions change, budgets vanish, and priorities shift. Eventually, the ship becomes truly alone, because even the memory of it becomes optional. This answers a callback from earlier chapters. Sustaining multi-generation continuity is not just funding, it is maintaining meaning across centuries of silence, while the home world becomes a different civilization that no longer feels responsible. Now add compounding failure probability across domains, because survival is conjunctive. Life support, genetics, industry, governance, and health must all succeed together. A single fatal weakness in any one layer can end everything, no matter how strong the other layers are. If each subsystem has a 99.9% chance of surviving a century, the combined chance over 10 centuries is not comforting. The math is not pessimism, it is multiplication. Small risks multiply because the timeline multiplies them. A generation ship is not one challenge. It is a stack of challenges that all must clear, again and again, without a reset button. The longer it flies, the more it resembles a tightrope walk performed in slow motion. Even if the ship survives, arrival creates a final trap. The descendants did not sign the launch document. They inherit the mission like an ancient debt, and debts are often rejected when the creditor is history. Consent becomes the arrival problem in human form. The crew at arrival may reject landing, reject contact, or reject the destination entirely. They may decide that the promised world is not worth the risk of changing everything they know. They may choose to remain in space, because space is the only home their culture has ever known. They may fear planets as hostile myths, places of crushing gravity, open sky, and diseases that live in dirt. The very idea of weather could sound like a threat. They may also arrive to a target that changed, because time changes everything. The destination system may be uninhabitable, already occupied, or politically dangerous. A star can flare, a planet can lose atmosphere, or another civilization can claim the same orbit. A generation ship cannot easily pivot once it commits. Its resources are optimized for cruising, not for colonization war, diplomacy, or rapid terraforming. Even a small change in requirements can be impossible when your economy is closed and your margins are thin. So the mission can outlive the species that launched it, yet still fail at the last step. The ship becomes a drifting archive, not a bridge. It carries languages, genomes, and stories, but it does not deliver them where they were meant to go. This reframes the silence again. If interstellar travel requires turning a society into a sealed, fragile experiment, many civilizations may refuse. They may look at the cost, not just in energy, but in social risk, and decide that staying home is rational. The laws of physics did not say no. They demanded time, and time demanded that minds remain coherent across centuries. That is a different kind of wall, and it is harder to engineer around. It is not the speed of light. It is the speed of cultural drift. The ship can keep its course through space, yet still lose its course through meaning. So the slow solution does not rescue the dream. It relocates the impossibility from engines to institutions and from propellant to purpose. The hardest component is not metal or fuel, but continuity, maintained without coercion and without collapse. We are left with a bleak symmetry. Fast travel is punished by energy and bullets. Slow travel is punished by entropy and the human condition. Either way, the universe extracts a price that feels designed to keep minds apart. Transition forward. If ships cannot reliably cross the Gulf, maybe something else can travel instead. Information can be beamed without life support, without genetics, and without mutiny, and it can ride a narrow cone of light across the dark. But even information cannot outrun light, and light imposes its own cruel delay. A message sent today arrives as an artifact of a past that cannot be corrected. The further it goes, the less it is a conversation, and the more it is a fossil. If the universe is crowded with intelligence, it may still be quiet to us. Not because nobody speaks, but because every message arrives as history, not conversation. We may be surrounded by minds, and still live inside a silence made of distance and time. If the universe is full of minds, why has the sky stayed silent? Are we alone, or simply unreachable? Chapters 5 and 6 showed the travel bind, and the bind was not philosophical. Go fast and the void becomes gunfire, because dust grains carry kinetic energy like bullets. Go slow and time becomes the weapon, because biology, politics and patience decay long before the destination arrives. Now we pivot from ships to signals, because information seems lighter than metal. A beam can cross the gulf without life support, shielding or mutiny, and it does not need to break at the far end. In the imagination, communication feels like the clean loophole, a way to touch another world without paying the full fare. But the same wall returns in a quieter form. Light does not only limit travel, it limits relationship because relationship depends on shared moments. The speed of light is not just a number in a textbook, it is the universe's enforced tempo. Start with latency, because latency sets the emotional scale of contact. A message to a star 100 light-years away needs 100 years to arrive, even if it is a perfectly aimed laser. A reply needs another 100 years, because causality demands a round trip and physics refuses to bargain. A simple hello becomes a 2-century loop, even when everyone cooperates and nobody hesitates. 2 centuries is longer than most governments, longer than most languages, longer than most technological eras. It is longer than the time between the first steam engines and the first satellites, which should sharpen the intuition. Civilizations can change beyond recognition while the photons are in flight, and the sender may not survive to hear the answer. So interstellar communication is not dialogue. It is archaeology conducted at the speed of light, where every message is a fossil of a past state. When we look outward, we are already looking backward, and any reply we send becomes a time capsule. Even at 10 light-years, the delay is 20 years round trip, which is still a career. At 50 light-years, it is a century, which is a cultural reset, even for a stable society. The calendar itself becomes part of the barrier, because meaning depends on timing. This matters for the central question. If aliens cannot arrive, could they at least coordinate, warn, or negotiate with us? And could we do the same? Relativity allows messages, but it denies shared time, and shared time is what makes agreements feel real. The universe permits announcements, yet it punishes conversation, because conversation is feedback, and feedback is slow. Then comes the second barrier, which is not time, but faintness. Signals do not travel like arrows, they spread like ripples, and ripples dilute. In free space, power density falls with the inverse square law, because the same energy must cover an ever-growing sphere. Double the distance and the same transmitter becomes 4 times dimmer at the receiver. Multiply the distance by 10 and you lose 100-fold, which is the kind of scaling that eats civilizations. At interstellar ranges, inverse square loss is not a detail. It is the main cost driver, because every extra light year demands disproportionate transmitter power or disproportionate collecting area. A civilization can try brute force. It can broadcast isotropically, like a lighthouse shining in all directions, and trust that someone will eventually drift into the beam. But isotropic broadcasting is a wasteful strategy at galactic scale, because most of the energy goes into empty sky. Only a tiny fraction hits any target, and even that fraction arrives thin to a whisper. So practical interstellar messaging demands gain. Gain means antennas, apertures, and narrow beams that concentrate power into a small solid angle, like cupping hands around a candle. Radio dishes do this with size and wavelength, because a larger aperture compared to wavelength produces tighter directionality. Optical systems do it with mirrors and lasers, trading engineering precision for tighter divergence and higher carrier frequency. A narrow beam changes the economics, but it creates a new problem. You must already know where to point, and you must keep pointing for a long time while planets move and stars drift. The beam is efficient precisely because it is unforgiving, and the sky does not hold still. This is where contact becomes coordination, not just transmission. The sender and receiver must share a schedule across decades of uncertainty, and they must share a target definition across astronomical motion. Even the star's proper motion matters, because a beam aimed at yesterday's coordinates can miss tomorrow's planet. Even with a strong transmitter, the receiver still fights noise. Space is not silent, and the sky has a temperature, which is a real physical measure in radio astronomy. At radio frequencies, there is the cosmic microwave background, a near-uniform hiss left over from the early universe. There is also galactic synchrotron emission that rises at low frequencies, produced by electrons spiraling in magnetic fields. Stars add their own radio noise through flares, plasma, and magnetospheres, and that noise can spike without warning. Planets can contribute auroral emissions, and those can mimic structured bursts because nature likes repetition. Receivers also add noise, because electronics have thermal limits and resistors jitter with heat. Every amplifier has a noise figure, and every system has a noise floor, even in the best cryogenic designs. Detection is therefore a signal-to-noise problem, not a romance. You can win by increasing received power, reducing bandwidth, integrating longer, or cooling the receiver, and each method has a signature in the engineering. But each lever has a cost, and the costs stack. More power demands more infrastructure, more heat management, and often more political will. Narrower bandwidth reduces information rate, because a thin channel carries fewer bits per second. Longer integration demands stable pointing and stable frequency, because drift smears the signal across bins until it vanishes. This is why SETI often searches for narrowband carriers. A very thin spectral line stands out against broadband noise like a needle in a warm haystack, and it can be found with relatively modest computation. Historically, early searches leaned on this logic, from Project Ozma onward, because narrowband was the most unambiguous engineered-looking feature we could afford to scan. Yet a narrowband beacon is information poor by design. It says someone is there, but it cannot easily carry rich content without spreading into the noise, and content is what we actually want. The signal that is easiest to notice is rarely the signal that is easiest to understand. Information theory makes this trade explicit. For a given power and noise level, channel capacity limits how many bits per second can be sent reliably, and the limit is mathematical. If you want high data rates across light years, you must raise power, increase aperture, or accept higher error rates. Physics does not care about meaning, only about photons and statistics, and it keeps the ledger honestly. Encoding can help, because error-correcting codes trade redundancy for reliability, and modern codes can approach theoretical limits. But redundancy also consumes bandwidth, and bandwidth is already scarce at distance because the receiver's sensitivity is finite. A civilization can compress, interleave, and code, but it cannot cheat Shannon and it cannot compress randomness. At long range, detectability and richness pull in opposite directions. A beacon wants to be simple, persistent, and unmistakable, while a library wants to be dense and efficient. The more you pack into the signal, the more you risk hiding it inside the noise you cannot control. Then there is confusion, which is different from noise. A signal can be strong enough to detect yet still ambiguous, because the universe produces patterns for free. Natural astrophysical processes can produce pulses, drifts, and repeating structures, especially when magnetism and rotation enter the picture. Pulsars were once mistaken for beacons because nature can look engineered when it's stable and periodic. The first detections were nicknamed with a joke about little green men, and the joke carried a warning. To claim an artificial origin, you need signatures that resist natural explanation, and you need them across time. Narrowband tones, Doppler-consistent drift, and structured modulation help, but none are perfect. You also look for improbably precise frequency stability, or for patterns that encode mathematics in a way that resists natural mechanisms. Even then, the burden of proof is heavy, because the sky is vast and our biases are eager. Doppler shift complicates everything. Planets rotate, orbit, and accelerate, and those motions smear frequencies unless you track them precisely, which requires assumptions about the transmitter's world. The transmitter has its own motion too, and the relative velocity changes over years as stars orbit the galaxy. A receiver must search not one frequency, but a band of possible drifts, and it must do so across many sky positions. That search space becomes enormous when you include unknown orbits, unknown ephemerids, and unknown clock standards. A missed drift rate can hide a real signal inside the noise, like a melody played between the keys. This leads to the synchronization problem. Even if a civilization is shouting, you must be listening at the right time, in the right direction, at the right frequency, with the right drift correction. A narrow beam might sweep past Earth for minutes, then never return for decades, because the sender is scanning or sharing the transmitter. A receiver that looks away at the wrong moment will conclude there is silence. Listening itself is expensive. Large collecting area is rare, and telescope time is contested even on Earth, where every hour has competitors. A galaxy-wide search is therefore not just a technical challenge, it is a scheduling and probability challenge, where absence of evidence is not evidence of absence, and where the null result is always ambiguous. The sky can be quiet for us while still being busy for someone else. This is the SETI implication that cuts against intuition. Silence can mean nobody is there. Silence can also mean the signals are weak, narrow, rare, misaligned, mistimed, or encoded in ways we're not yet searching. The difference between empty and missed can be a few minutes of pointing. There is also the possibility of deliberate quiet. A civilization may choose low detectability for safety, because broadcasting is a form of self-disclosure, and self-disclosure is irreversible. That connects back to earlier chapters about restraint, where survival can reward caution over curiosity. If travel is hard and risky, then communication becomes the main interface, and even that interface may be used cautiously. The loudest society is not necessarily the longest lived, and the most advanced may be the most careful. Now connect communication back to travel, because travel without communication is not a mission. Interstellar projects require coordination across distance, and coordination requires timely feedback, which light refuses to provide. A probe launch to another star cannot be joystick controlled, no matter how cinematic the idea feels. At 4 light years, a command takes 4 years to arrive, and the telemetry takes 4 more years to return. That is an 8-year control loop, which is not control at all, and it breaks every instinct we have about piloting. It is delayed influence over a system that has already changed, and the change can be fatal. At 50 light years, the loop is a century. Any attempt at real-time piloting becomes absurd, because the target environment evolves while you wait, and your map becomes history. Even the star's activity cycle can shift, turning a safe approach into a radiation storm. So interstellar probes must be autonomous. They must navigate, diagnose, repair, and adapt without human intervention for decades or centuries, and and they must do it with limited mass and limited power. Autonomy is not a software feature. It is a requirement that multiplies mission complexity, because the probe must handle unknowns without a support team. This is also a rescue problem. If something fails en route, there is no quick fix and no spare ship behind it, because distance turns logistics into myth. A failure report arrives years after the failure happened, and the diagnosis arrives after the craft has already improvised or died. By the time the homeworld understands the problem, the probe may already be dead, drifting cold between stars. Even if the probe survives, arrival creates the same delay and the same isolation. If it finds something unexpected, it cannot ask what to do next because the question itself takes years. It must decide because the universe will not wait for permission. That decision must be right on the first try because the second try arrives too late and opportunity windows close. A flyby is a single pass and a landing is a single commitment. The same logic applies to crewed missions, only with higher stakes. A generation ship cannot call home for medical advice in real time, and it cannot outsource ethics to a distant committee. It cannot negotiate a crisis with Earth on a human timescale, and it cannot receive new parts, new people, or new orders. So communication delay reinforces the isolation described in Chapter 6. The ship is not only physically alone, it is temporally alone, living in a different now. Even if two civilizations try to coordinate a meeting, the planning horizon becomes extreme, and the uncertainty becomes structural. You must predict trajectories, politics, and intentions across decades of delay, and you must do it without shared updates. Misunderstandings become baked in, because clarification arrives after the context has shifted. Diplomacy becomes a chain of letters, not a conversation, and the tone can be misheard for generations. This is why the film calls it the loneliness of light. Light carries information faithfully, yet it carries it too late, and lateness changes everything. The medium is honest, but the schedule is cruel. Now return to the engineering of detectability, because it shapes what contact would look like. If beacons exist, they likely favour simple, robust signatures, because robustness survives ignorance. A continuous narrowband tone is easy to detect, but it is also easy to drown in nature's noise if the receiver is unlucky. A pulsed beacon can improve detectability by concentrating energy, so the peak power rises above the background. But pulsing introduces timing, and timing introduces another synchronization axis. You must know the repetition period, the duty cycle, and the clock stability, and you must search across possibilities. Clock stability is not trivial across centuries. Even atomic standards drift relative to each other when you cannot compare them frequently, and when you cannot agree on what now means. A transmitter might encode time using astrophysical references, like pulsar periods or spectral lines, because those are shared landmarks. Yet the receiver must guess the same reference scheme, and it must recognize the landmark through its own noise. The very thing meant to be universal can become another layer of ambiguity. Pointing is equally unforgiving. A laser beam can be microradians wide, which is powerful and efficient, and visually it's almost nothing, a pencil-thin thread in blackness. But microradians at dozens of light years means a miss by astronomical units, because tiny angles become huge distances. A small pointing error can send the beam between planets without touching them, and the receiver will never know it was almost chosen. So a tight beam implies either prior knowledge of the target's ephemeris, or a scanning strategy that paints the system repeatedly. Scanning spreads energy thin again, returning to the inverse square trap and the tyranny of limited power. This is the core loop. To be heard, you must concentrate power. To concentrate power, you must aim precisely. To aim precisely, you must already share knowledge, and knowledge is what you are trying to exchange. This is why contact is hard even when everyone is friendly. The physics of propagation demands coordination before coordination is possible, and that paradox is not emotional. It is geometric, and it is statistical, and it is relentless. Now widen the frame to the Milky Way. The galaxy is 100,000 light-years across, which is also 100,000 years across, and that number should be felt as a weight. A signal crossing the disk is a message from a deep past, launched before our species wrote its first records. By the time it arrives, the sender might be extinct, transformed, or uninterested, and the receiver might not exist either. So even if the galaxy is crowded, it can still feel empty locally. We are not only separated by distance, we are separated by non-overlapping eras, like ships passing in different oceans of time. This reframes the opening hook. The sky can stay silent not because nobody speaks, but because the speaking is out of phase with our listening. The harshest version is timing cruelty, where the overlap window is small and easy to miss. A civilization may broadcast for 1,000 years, which feels long to them, and may even be remembered as an age. Yet 1,000 years is only a 1% slice of 100,000-year crossing time, and the geometry is unforgiving. Their beacon can easily miss us in time as well as space, even if it is powerful. Humanity's own radio leakage illustrates the problem in miniature. Our loudest unintentional emissions came from high-power broadcast and radar, and they have been fading as we move to fibre, satellites, and efficient protocols. Our detectable window may be brief, and we may not even know when it closes, because quiet feels like progress. Other civilizations may have similar windows, opening and shutting like fireflies across the disk, each one bright to itself and dim to others. So SETI searches a moving target. It tries to catch brief technological phases, not eternal signatures, and it does so with limited time. There are strategies to improve odds. Look for persistent beacons, search for wideband bursts, and monitor many stars repeatedly, because repetition is a clue. But every strategy trades depth for breadth. You can stare at one star deeply, or glance at many stars shallowly, and both choices have regret. And the noise environment changes with frequency. Low frequencies suffer galactic noise and ionospheric limits, which bend and absorb signals near Earth. High frequencies suffer atmospheric absorption and pointing precision, and even water vapor becomes part of the problem. Optical SETI trades radio noise for photon counting and background starlight. A laser pulse can stand out, yet only if you're looking at the right star at the right moment, with detectors fast enough to notice nanosecond flashes. The visual is almost cruel, a dark dome of stars, and somewhere inside it a single engineered blink. Even if we detect a signal, interpretation is slow. Decoding requires assumptions about encoding, symbols, and shared mathematics, and it requires patience under uncertainty. A first message might be designed to be universal, using primes, spectra, or geometric patterns, because those are common to physics. Yet universality is not guaranteed, and misreading is easy, especially when you do not know the sender's goals. What looks like a greeting could be a calibration sequence, and what looks like noise could be a compressed archive. Then the delay returns again. If we respond, our response arrives decades later, and their clarification arrives decades after that, and the rhythm never improves. By then, our own society may have changed its priorities, its institutions, and its patience, because human attention is not built for century-long threads. The conversation can die without anyone choosing to end it. It can simply fail to synchronize, like two clocks that never quite align. This is where communication and travel collapse into the same verdict. If you cannot coordinate in real time, you cannot build interstellar systems that depend on feedback, and feedback is what makes complex projects safe. Beamed propulsion, discussed earlier, becomes harder under this lens, even if the physics of thrust works. A laser sail needs precise tracking and sustained power over long durations, and the beam must stay locked as the craft accelerates away. If the sail is light years away, you cannot adjust the beam based on immediate telemetry. Your corrections arrive years late, after the sail has already drifted and the miss compounds. Destination-side braking has the same problem. If you rely on infrastructure at the target, you must trust it to exist and function when the craft arrives, and you must trust it without updates. Trust across light years is not trust in character, it is trust in continuity, maintenance, and politics across decades of delay. So even purely robotic exploration becomes a bet placed far in advance. The bet cannot be hedged with quick updates, because the universe denies quick updates and it denies second chances on short notice. This deepens the central question in a new way. The laws that isolate travellers also isolate planners, allies, and rescuers. The universe is not only hard to cross, it is hard to manage across, because management is feedback, and feedback is slow. That leaves a final unsettling possibility. Perhaps the galaxy is full of signals, but they are not meant for us, and they were never meant to be found by strangers. They may be aimed at known partners, using narrow beams and private schedules, optimized for efficiency rather than discovery. To outsiders, that looks like silence. Or perhaps the dominant mode is passive, like artifacts and probes that wait, because storage does not suffer inverse square loss. A message can be placed near a star or near a planet, and it can sit there for 1,000,000 years without fading. Yet even that returns to travel. To find stored messages, you must go there, and going there reopens every barrier we have already stacked, from energy to time to risk. So the loneliness of light is a complete loop. Communication seems like the easy alternative to travel until you price time, power, noise, and coordination. Relativity does not forbid contact. It turns contact into delayed evidence, and it turns evidence into a puzzle because the clues arrive out of order with our lives. If the universe is crowded with intelligence, it may still be quiet to us. Not because nobody speaks, but because light makes every exchange arrive too late. Transition forward. If light is too slow for conversation, then the mind reaches for forbidden shortcuts. Next, we ask whether space-time itself can be bent. Wormholes, warp drives, and the seductive cheats that promise to outrun the loneliness of light. If light is too slow for conversation, the mind reaches for forbidden shortcuts, and the imagination starts drawing doors where physics draws walls. Wormholes and warp drives feel like the one clean escape from distance, because they promise arrival without centuries and contact without the loneliness of light. General relativity invites the temptation, because it is not just a theory of gravity pulling on masses, it is a theory of geometry itself, of space-time bending, stretching, and tilting under energy, pressure, and motion. In Einstein's picture, planets do not feel a force in the old sense. They follow the straightest possible paths through a curved arena. That arena can behave in ways that look almost like magic when the conditions are extreme. Space can stretch while time slows, and clocks can disagree depending on their speed and depth in gravity. Paths that look impossible in flat space can exist, because straight is no longer what our intuition expects. The key is that relativity forbids local faster-than-light motion through space-time. No rocket, no engine, no particle can outrun a light beam in its immediate neighbourhood. Yet relativity does not obviously forbid space-time itself from changing shape, and that loophole is why the most serious cheats are written in the language of Einstein. We treat them respectfully, because the equations allow them on paper, and because physics has a history of turning once impossible ideas into engineering. The question is whether the universe allows the required matter and stability, rather than merely allowing a solution in symbols. Our central question remains unchanged. Do the fundamental laws of physics make it effectively impossible for any intelligent civilization to reach Earth? Start with the warp drive concept, because it sounds like a legal trick hidden inside a technicality. In 1994, physicist Miguel Alcubierre found a metric, a specific way to write spacetime's geometry, with a moving bubble of flat space. Inside the bubble, a ship is locally at rest, surrounded by calm spacetime, and it never exceeds light speed. Visually, it is easy to see why this seduces us. Imagine a grid painted across the universe, like lines on a rubber sheet, and then imagine those lines flowing like a current. The bubble moves by expanding space behind it and contracting space ahead, so the ship rides the distortion the way a surfer rides a wave. Globally, the bubble can translate faster than light relative to distant observers, even though nothing inside breaks the speed limit locally. The ship does not break the rules in its own neighbourhood. Space-time does the moving, an elegant dodge that seems to respect the letter of relativity. This seems to answer the energy abyss from Chapter 4, because the ship is not accelerating to near C in the usual way. It seems to avoid the bullet problem from Chapter 5 because the ship is not ploughing through the medium at relativistic speed. It seems to avoid the generation ship trap from Chapter 6, because travel time can be short enough to fit inside a lifetime. For a moment, the sky feels less silent, as if the universe has been hiding a back door. If space-time can be engineered, then distance is not a prison bar. It becomes a material, like steel or glass, that a civilization might shape into tools. Then the cost appears, and it is not a small footnote tucked into a technical appendix. The Alcubierre metric requires negative energy density in the warp ring, concentrated in a shell around the bubble. Not just a lot of energy, but energy of the wrong sign, stress energy that behaves unlike any ordinary matter we can hold. In general relativity, energy conditions are the guardrails that keep geometry from becoming too pathological. They encode the intuition that mass energy is positive, that observers measure non-negative energy density, and that gravity generally attracts rather than repels. Warp bubbles violate the weak and null energy conditions, which means they demand exotic stress energy that pushes space-time the wrong way. Negative energy is not pure fantasy, because quantum fields allow it in limited, carefully constrained forms. The Casimir effect, measured in laboratories, produces regions where the energy density is lower than the vacuum between closely spaced conducting plates. Squeezed quantum states of light can also create brief negative energy fluxes, like a momentary dip below a baseline that is usually untouchable. But quantum field theory adds a second set of guardrails, and they are tighter than the first. Quantum inequalities restrict how much negative energy can exist and for how long, and they tie the magnitude to the duration and size of the region. The more negative you make it, the shorter the allowed duration, and the smaller the region that can sustain it. This is the first door closing, and it closes with a quiet mathematical click rather than a dramatic slam. The warp drive needs sustained, macroscopic negative energy arranged with precision, like a sculpted ring that holds its shape while it moves. The quantum vacuum allows tiny, fleeting deficits that are hard to scale, and scaling is exactly what a starship requires. Even if a civilization could accumulate negative energy, the geometry fights back in another way. Many warp metrics create enormous energy densities at the bubble wall, where curvature changes rapidly over a short distance. The gradients are violent, and the stress energy becomes extreme at the boundary, as if the universe is charging interest on the distortion. That boundary is not a harmless shell you can treat like armor plating. It behaves like a horizon structure, because signals from inside may not reach the front edge once the bubble is superluminal. In many formulations, the ship cannot control the bubble once it forms, because the front of the bubble is causally disconnected from the interior. The horizon issue also connects back to Chapter 7, where communication delays and control limits become existential. If you cannot send control signals across your own bubble boundary, you cannot pilot in any normal sense. A vehicle that cannot be steered is not a vehicle. It is a one-shot event, launched like a stone and guided by hope. Some papers propose modified warp metrics to reduce energy demands, and the effort is serious rather than fanciful. They reshape the bubble, thicken the wall, smooth the velocity profile, or trade one kind of stress energy requirement for another. The improvements are real in the math, but the requirements remain extraordinary, and the sign problem does not simply vanish. Even optimistic estimates still imply astronomical energy scales, sometimes comparable to planetary masses when translated into equivalent energy. You're not paying with chemical fuel or even fusion fuel. You're paying with space-time engineering that rivals stellar processes, an invoice written in curvature, not in kilograms of propellant. Then comes the instability problem, because quantum fields do not sit quietly on curved backgrounds. Horizons and rapid curvature changes can create particle production, the way black holes produce Hawking radiation in theory. Vacuum fluctuations can be amplified, dumping energy into the bubble wall and turning the boundary into a furnace of unpredictable back reaction. In some analyses, the energy density near the front edge diverges as the bubble approaches superluminal speeds. That suggests a self-protecting mechanism built into the equations. The closer you get to the forbidden regime, the more the vacuum punishes you, as if the universe is enforcing its own speed limit with escalating penalties. This is not a proof of impossibility, and physics is careful about claiming final answers. Yet it is a warning that feels structural rather than accidental. It is like balancing a pencil on its tip in a hurricane, possible as a configuration, but not as a stable state you can rely on. Now we widen to causality, because faster than light is never just about speed. In relativity, FTL-like behavior often implies time travel in some frame, because simultaneity is not absolute. If you can arrive before light, you can often arrange closed time-like curves where future and past fold into a loop. Closed time-like curves are not a storytelling flourish or a Hollywood garnish. They are a direct consequence of combining FTL with the relativity of simultaneity, which allows different observers to disagree about the order of events. Two observers in relative motion can weaponize that disagreement into paradox, turning arrive early into arrive before you left. That brings back the unresolved question from Chapter 3, where the universe's rules seem to protect consistency. Are loopholes blocked because they violate causality, even if they satisfy the local equations? Many physicists suspect a deep prohibition, sometimes called chronology protection, as if time itself has an immune system. Chronology protection is not a single theorem we can point to and end the debate. It is a pattern in the math, and in our best theories, repeated across many attempted constructions. When you try to build time machines, infinities and instabilities often appear, like warning lights that turn on before the device can be switched fully on. The vacuum seems to react violently near the formation of a time loop. Quantum stress energy can blow up, or the required matter becomes unphysical, or the geometry becomes so sensitive that tiny disturbances destroy it. The message is consistent. Causality is not easily negotiated, and the universe seems unwilling to sign a contract with contradictions. So warp drives face a triple lock that is hard to pick. They require negative energy that quantum theory ration cards into microscopic fleeting amounts. They create horizon and control problems that break engineering intuition, because the pilot cannot reach the steering wheel. They flirt with causality violations that invite instability, as if the price of speed is a crack in time. We let the hope linger, because the equations are real, and because science advances by testing the edges. Then we move to the second cheat, which is older and even more seductive. Wormholes promise not speed, but a shortcut, and shortcuts feel less like rule-breaking and more like clever navigation. A wormhole is a tunnel connecting two distant regions of space-time, like a handle attached to a surface that lets you cross without travelling the long way around. In the simplest picture, you step in here and step out there, and the journey is short because the path through the tunnel is short. You never exceed light speed locally because you're not racing across normal space. General relativity contains wormhole solutions, including the Einstein-Rosen bridge, discovered in the 1930s as physicists explored black hole geometries. Historically, these bridges emerged from the same mathematical curiosity that revealed black holes themselves, but the classic bridge is not traversable because it pinches off too fast, and anything trying to cross is trapped behind horizons. Traversable wormholes require a throat held open against gravity, like holding open a tunnel in a mountain that constantly tries to collapse. That again demands exotic matter with negative energy density, because ordinary matter makes gravity attractive and squeezes the throat shut. The same energy conditions are violated, and the same quantum inequalities return, now acting like a strict building code. The wormhole throat is a stress test for physics, not just a geometric sketch. It must resist collapse, resist tidal forces, and remain stable under perturbations, including the gravitational influence of nearby masses. Even small disturbances can change the geometry and trigger a pinch-off, because the throat is balanced between competing demands. Tidal forces are not optional details you can ignore for narrative convenience. A wormhole that is small enough to be portable tends to have huge curvature concentrated in a small region. Huge curvature means spaghettification, differential gravity that stretches and compresses, unless the throat is enormous, and an enormous throat is an enormous engineering project. Stability is the next door closing, and it closes through feedback rather than brute prohibition. Even if you could create a wormhole, keeping it open is a continuous fight, because the geometry responds to what passes through. Matter passing through adds energy and momentum, which can destabilize the throat, and the act of using it can destroy it. Quantum effects add another hazard that is subtle in description, but brutal in consequence. Fields in curved space-time can generate negative and positive energy fluxes that back-react on the geometry, changing the curvature that created them. The wormhole becomes a coupled system of gravity and quantum vacuum, with feedback that can run away if the balance is even slightly off. Then causality returns, because wormholes are time machines in disguise once you allow their mouths to experience different histories. If the two mouths experience different time rates, due to motion or gravity, they become time-shifted relative to each other. Passing through can send you into the past of the outside world, not by magic, but by time dilation. This is not speculative hand-waving, because time dilation is already part of our everyday technology. GPS satellites correct for both special and general relativistic time shifts, because otherwise navigation drifts by kilometers. A wormhole mouth taken on a relativistic trip can come back younger, creating a temporal offset between the mouths that is as real as any clock reading. Once the offset exists, closed time-like curves can appear, and the geometry offers you a loop. You can go through the wormhole, then return through normal space, arriving before you left, at least in some external frame. Paradox is not guaranteed, but the possibility is built in, and physics becomes uneasy when contradictions are allowed to become engineering. Again, many analyses suggest the universe reacts by destabilizing the configuration before the paradox becomes operational. Quantum stress energy near the would-be time machine can diverge, or fluctuations can grow without bound, as if the vacuum is trying to tear the loop apart. The system may self-destruct before any traveller can exploit the timeline. So wormholes share the warp drive's core problem, even though the story feels different. The math allows them, but the physical ingredients look forbidden or unscalable. Negative energy is the recurring price tag, and quantum theory keeps refusing the payment, offering only tiny coupons where a civilization needs a fortune. Now address the third cheat, because audiences carry it from science fiction, and because the word itself sounds like a secret corridor. Hyperspace-like shortcuts imagine a higher dimensional route, where you leave our space, travel a shorter distance, then re-enter. The visual is always the same, a ship slipping off the map, then returning far away. In modern physics, extra dimensions appear in some theories, especially those that try to unify forces. Yet they are not open highways in the usual models. They are typically compactified, curled up at tiny scales so small that ordinary matter cannot move through them the way a ship moves through space. Even if large extra dimensions existed, access would require energies far beyond current reach, because you would need to excite modes that couple to the extra geometry. Brain-world scenarios sometimes allow shortcuts through a bulk, but the same causality and energy constraints tend to reappear in new clothing. A shortcut that beats light in our brain still behaves like FTL in the effective theory, and effective FTL still threatens causality, because the light cone is the real boundary, not the name of the route. If you can send influence outside the light cone, you can often build signaling loops by combining motions and frames. The universe does not care whether you call it hyperspace or geometry. It only cares about causal structure. So the pattern holds across cheats, and the repetition is itself a clue. Each one is a different attempt to outrun the same wall, and each one runs into the same deep costs. The wall is not just technological, it is woven into energy, quantum fields, and time, and it shows up whenever we try to bend the rules without breaking them. Now we do the engineering reality check, because in principle is not a mission plan and never has been. Even if exotic matter exists, you must create it, confine it, and shape it into a stable configuration. You must do so with precision that makes particle accelerators look crude, because the geometry depends on the full stress energy tensor, not just a fuel tank reading. A warp ring or wormhole throat is not a passive object you build once and then trust forever. It is a dynamic space-time configuration that must be actively stabilized, because small perturbations can grow. That implies sensors, feedback, and control at relativistic field strengths, and it implies tolerances that feel closer to metrology than to mechanics. It also implies error bars smaller than atomic scales over macroscopic distances, because the bubble wall is defined by steep gradients. A tiny asymmetry could turn a smooth distortion into a violent curvature spike. When the medium you are shaping is space-time itself, the usual engineering trick of add more material does not apply. Containment is its own paradox, because negative energy is not a substance you pour into a tank. It is a property of quantum states, often fragile and easily disrupted by interactions with the environment. The act of measuring and controlling it can destroy the state you need, because quantum systems do not like being pinned down. Then there is the energy scale again, which echoes Chapter 4's verdict with a darker tone. Near-light travel demanded civilization-scale power over long durations. Space-time engineering demands something worse, because it demands not just energy, but the ability to shape stress-energy tensors at will, like writing a custom gravitational field with the precision of a circuit. Even optimistic revisions that reduce total energy still require extreme densities, concentrated in narrow regions. They require configurations that would crush ordinary matter or radiate catastrophically if anything goes wrong. The cheat becomes a demand for new physics plus perfect engineering, and perfection is not a resource any civilization can assume. We also cannot ignore the bullet problem entirely, even if the warp bubble avoids ordinary drag. A warp bubble moving superluminally could sweep up particles at its front edge, piling them into a compressed energetic layer. Some analyses suggest dangerous radiation bursts when the bubble stops, dumping accumulated energy forward like a shotgun blast of high-energy particles. That creates an arrival hazard that mirrors the braking problem, only in a different costume. You can reach the destination quickly, then sterilize it with your own wake, turning the target system into collateral damage. A shortcut that cannot arrive safely is not a rescue from the travel bind. It is a different way to fail. So the audience's hope narrows to a final refuge, and it is the refuge we always keep for the unknown. Maybe a super advanced civilization has mastered quantum gravity, and maybe our current constraints are temporary, like pre-rocket skepticism about leaving Earth. Maybe the negative energy bookkeeping changes when space-time itself is quantized and the guardrails are redrawn. We grant the maybe someday clause because honesty requires it, and because physics is incomplete at the Planck scale. None of these constructs are mathematically forbidden in all forms, and our theories are stitched together from domains that do not yet fully agree. Quantum gravity could surprise us, and surprises are how science grows. But the sober conclusion is still heavy, and it becomes heavier the more carefully we examine the details. With known physics, the required negative energy is constrained, the stability is doubtful, and causality violations loom. The doors do not slam from prejudice. They close from repeated accounting, as if every ledger ends in the same deficit. This matters for the opening hook because silence is not just a poetic mystery. If the universe is full of minds, why has the sky stayed silent, with no visitors and no unmistakable signals? One answer is that the cheats are not real in practice, even if they are real on paper, and that practical reality shapes the history of civilizations. Civilizations may dream of wormholes the way we dream of perpetual motion, beautiful diagrams, elegant promises, and a quiet refusal from nature. The equations can be written, but the universe charges hidden fees in stability, causality, and quantum constraints. If you cannot pay them, you remain trapped in the slow economy of light, where distance is paid in years. So the central question sharpens, and it sharpens into something almost philosophical. It is not whether a clever species can imagine a loophole, because imagination is cheap and infinite. It is whether nature supplies the exotic ingredients and the stability needed to use it. And so far, every serious analysis points the same way. We end where we began, with respect for the temptation, and respect for the rules that resist it. General relativity is flexible enough to hint at escape, and it does so with seductive clarity. Quantum field theory is strict enough to ration the escape into near nothing, and it does so with constraints that feel like a cosmic budget. Even if a civilization could launch, and even if it could cheat, the universe itself is changing. Expansion stretches the gaps wider, and the horizon of reach recedes with time, turning today's reachable galaxies into tomorrow's unreachable islands. The silence may not be a lack of life. It may be a map whose distances grow faster than any traveller can close them. If the universe is full of minds, why has the sky stayed silent? Are we alone, or simply unreachable? Chapters 2 through 8 built a prison from distance, light speed, energy, hazards, time, and failed shortcuts. Now we zoom out again, because the prison is not only between stars, it is written into the universe's large-scale geometry, and it changes with time. On the bigger scales, the bars are not metal or stone, they are equations, and they reshape the map while you travel. Start with the simplest observation, because it is the one that rewrote modern cosmology. Distant galaxies show redshift, and the redshift scales with distance in a clean trend. The Hubble, Lemaitre law summarizes it in one line. The farther a galaxy is, the faster it recedes from us. In spectra, familiar atomic lines slide toward longer wavelengths, as though the universe is quietly lowering the pitch of every distant beacon. This recession is easy to misread, so we correct the intuition before it hardens. Galaxies not mostly flying through space like shrapnel from a central blast. Space itself expands, and the expansion stretches the distance between unbound systems. In that picture, recession velocity is not a local speed limit violation. It is the rate at which the metric distance grows. General relativity does not treat space as a passive stage. It is part of the dynamics, and it can evolve. That distinction matters for the central question, because it changes what catching up even means. A ship can move through space at some speed below light, yet the space between islands can also grow while the ship is in transit. The target can recede without firing an engine because the map itself is stretching. The traveller is not only crossing a gap, the gap is also being rewritten under the traveller's feet. On small scales, gravity and binding energy win, and the expansion is irrelevant. Inside a galaxy, stars orbit under gravity, and the Milky Way does not expand like a balloon. Inside solar systems, atoms and planets do not drift apart from cosmic expansion. Expansion is a large-scale effect that becomes visible only when gravity no longer holds structures together. In practical terms, electromagnetic bonds and gravitational wells create rigid neighbourhoods where the cosmic stretching cannot pry things apart. So we separate the universe into regimes, because travel depends on which regime you are in. Bound structures behave like stable neighbourhoods, where distance is mostly fixed. Unbound intergalactic space behaves like a moving walkway that can run against you. The walkway is slow nearby, then faster farther out. Visually, imagine a grid painted across the cosmos, with galaxies pinned to it like beads. Then watch the grid lines lengthen between the beads. The Hubble. Lemaitre law makes that walkway quantitative. Recession velocity is proportional to distance, with a constant of proportionality called h0. h0 is measured in kilometers per second per megaparsec, a unit that sounds strange until you feel it. It means every extra megaparsec adds another slice of recession speed, as if the universe charges interest on separation. At a few megaparsecs, the recession is modest, and a fast ship could still close the gap. At hundreds or thousands of megaparsecs, the recession becomes enormous. Eventually, the recession rate exceeds c, not because anything locally outruns light, but because the distance grows faster than light can cross it. This is the first cosmological punchline. There are galaxies we can see whose present-day recession rate is greater than light speed. Their ancient light still reaches us because it was emitted when they were closer, and because the expansion history changed over time. Photons can make progress even when the goalpost is moving, provided the early universe was kinder to pursuit. Seeing is not the same as reaching, and visibility is not the same as influence. Now add the second observation, because it turns expansion from a steady drift into a tightening trap. In the late 1990s, supernova surveys found that expansion is accelerating. The universe is not merely expanding. The expansion rate, in a specific sense, is being driven so that distant galaxies pull away faster over time. The discovery came from careful, almost humble work. Astronomers using exploding stars as calibrated candles, then noticing the candles were dimmer than a decelerating universe would allow. We name the driver carefully because the name can mislead. Dark energy is not a proven substance in a jar. It is an observed phenomenon, inferred from multiple lines of evidence, that acts like a persistent energy density of space. In the simplest model, it behaves like a cosmological constant, with negative pressure that makes expansion accelerate. Negative pressure is a technical phrase, but the plain meaning is sharp. As space grows, the energy does not thin away the way matter does, so the push does not fade. The evidence is not a single fragile measurement. Type IA supernovae map distance versus redshift, and show an acceleration signature. The cosmic microwave background encodes geometry and composition in its acoustic peaks. Large-scale structure and baryon acoustic oscillations trace how clustering evolved. Together they point to a universe dominated today by something that does not clump like matter. Even gravitational lensing and the growth rate of cosmic structure echo the same story, as though the universe is expanding with a hidden hand on the throttle. For travel, the key is not the label, but the consequence. If dark energy remains roughly constant, the far future approaches a de Sitter-like expansion. Distances between unbound galaxies grow exponentially with time. Exponential growth is the enemy of pursuit, because it turns a finite head start into permanent separation. A straight-line chase becomes a losing game, not because the ship slows, but because the arena itself accelerates away. This is where horizons enter, because horizons are the universe's hard boundaries on contact. We define two horizons, because they answer two different questions. The particle horizon is about what we can see now, given the universe's finite age. It marks the farthest region whose light has had time to reach us since the beginning. When we look near that limit, we're not seeing far away in the ordinary sense. We're seeing deep time, a record written when the cosmos was young. The event horizon is more severe, and it is the one that matters for alien travel. It is not about what we can see. It is about what we can ever affect, even with perfect patience and perfect technology limited by relativity. In an accelerating universe, there are regions whose light emitted today will never reach us. There are also regions we can see now that we will never be able to influence, because signals sent today cannot cross the expanding gap. The horizon is not a wall you crash into. It is a boundary in space-time, where later stops being enough. So the universe splits into two maps that look similar but behave differently. The visible universe is a record of what has already reached us. The reachable universe is the set of places we can still touch, in principle, with any future action. Accelerating expansion makes the reachable set smaller than the visible set, and it keeps shrinking. The sky can be crowded with lights, yet the causal map can be sparse, an atlas of places that are already slipping away. This is the second cosmological punchline, and it sharpens the documentary's tension. Even if the sky is crowded with civilizations, many of them are already outside our future light cone. Their existence could be real, and their stars could be visible, and yet no ship or signal launched now could ever arrive here. The cage is not only distance, it is causal structure. The silence might not be indifference, it might be geometry doing what geometry does. Now connect horizons back to the earlier prison bars because cosmology amplifies every one of them. Chapter 3's lightspeed wall becomes more final when the destination is receding. Chapter 4's energy abyss becomes worse when you must fight a growing separation, not just a fixed one. Chapter 7's loneliness of light becomes permanent when the round trip is not merely slow, but impossible. Even the most disciplined engineering begins to look small against a universe that changes the rules mid-journey. A civilization could imagine building a galactic empire, and within a galaxy, the expansion does not tear it apart. The Milky Way is gravitationally bound, and its stars remain in causal contact on human and stellar timescales. Even the local group is mostly bound, with the Milky Way and Andromeda on a collision course. Gravity can win locally, and it can stitch a small island against the cosmic tide. In a wide shot, you can picture it as a knot in a stretching fabric, tight, coherent, and stubborn. But the island is small compared to the ocean. Beyond the local group, galaxies participate in the Hubble flow more cleanly. Over time, more of them cross the event horizon and become unreachable forever. Their light can still arrive for a while, then it fades and redshifts, stretched to longer wavelengths and lower energy. The photons do not vanish, but they are diluted, like ink washed thin across an ever-expanding page. So the far future is not just empty of visitors, it is empty of information. Distant galaxies slip beyond causal contact, and their photons become too diluted and too redshifted to detect. The observable universe becomes a shrinking museum, where evidence of the wider cosmos disappears from practical measurement. Imagine a future night sky where the grand spiral islands are gone, leaving only local stars and a darkness that looks, misleadingly, eternal. This is not speculative poetry. It is a straightforward consequence of accelerating expansion under known cosmological models. If dark energy behaves like a cosmological constant, then in tens of billions of years, most galaxies outside our bound group will be gone from view. Not destroyed, not extinguished, but hidden behind a horizon we cannot cross. The tragedy is subtle. The universe can remain full, yet the accessible evidence can drain away. Now we return to the central question with a colder framing. Do the fundamental laws of physics make it effectively impossible for any intelligent extraterrestrial civilization to ever reach Earth? Even if we grant near-perfect propulsion within relativity, and even if we ignore the bullet problem and the generation ship problem, cosmology still limits the set of possible visitors. Many potential civilizations are not merely far, they are causally disconnected. The phrase "out there" becomes ambiguous, because some there is no longer part of our possible future. This is where the idea of recession faster than light needs careful handling again. A ship